Hello, everyone. Welcome to the February 2022 Ask Me Anything edition of the Mindscape podcast. I'm your host, Sean Carroll. It's been a while since we've done an AMA, since I do them every month except for January. So the last one we did was the beginning of December. And things have happened, right? I was in Boston last time we were doing an AMA, and now I'm back in Los Angeles. I have handed in the draft manuscript for my next book, which will be Volume 1 of the Biggest Ideas in the Universe series. Volume 1 is going to be called Space, Time, and Motion, and that's basically classical physics, broadly construed. So for those of you who don't know, the Biggest Ideas gimmick is I'm going to be teaching what I consider to be the biggest ideas in physics, even though I say it's in the universe. It's mostly physics we're talking about, a little bit of math in there. And the gimmick is that you aren't supposed to know any math or physics coming in. It is for a very broad audience, but I will teach you the math. So this is going to be a textbook certainly not a textbook, a book, a trade book, a popular book that is not afraid of doing the equations. And the trick there is that I'm not trying to teach you how to be a physicist. I'm not teaching you how to solve the equations like a working physicist or mathematician would have to do. I just want you to understand what the equations are saying. And that's actually enormously easier, as it turns out. So I will teach you what a derivative is and what an integral is and what vectors are and what tensors are. And with that, we'll go pretty far. We go through Newtonian mechanics, of course, but also Hamiltonian mechanics, Lagrangian mechanics, and the principle of least action, special relativity, general relativity, Einstein's equation, black holes, the Schwarzschild solution, with the equations there. So you have to be a little bit interested, a little bit motivated to do it, but I've been trying really, really hard to make it as understandable as I can. It certainly requires some effort on the part of the reader, but I think that if you're willing to put in the effort, almost anyone should be able to grasp this stuff at a real quantitative level. I mean, there's two obvious comparison books out there already. One is Leonard Susskind's series on the theoretical minimum. The difference between my approach and Suskind's is that he is kind of doing a more or less standard physics curriculum kind of thing. You know, here's Newtonian mechanics, and there is electromagnetism, and there's special relativity and quantum mechanics and so forth. So the topics are a little bit different because I can go faster because I don't need to worry about teaching you to be a working physicist, right? So it's not just physics 101, physics 102, etc. I can be a little bit more philosophical, talk about big picture ideas about space and time and what have you, but I can also get up to black holes pretty easily, which never happens. General relativity, as far as I know, is not part of the theoretical minimum series. And certainly in, this is only volume 1 of my series, volume 2, etc. will have quantum field theory and other things like that that are not in Suskind's books. As awesome as they are, I love those books, but it's a different kind of thing. The other obvious comparison is with Roger Penrose's book, The Road to Reality, which does do a lot of things. I would say it does it in a slightly quirky way. What can I tell you? Again, a brilliant, wonderful book. I think it would be hard for most people who didn't really know the math ahead of time to start from the beginning and go through that. So I'm both trying to be super duper pedagogical and understandable, and also trying to get to modern physics. I want you to know the basic ideas that a second-year graduate student in theoretical physics would know. You're not as facile, not as deep as a graduate student who's doing problem sets all the time, but you will hear the words and understand them and know what they mean and be able to look at the equations that bring those words to rigorous life and understand those as well. That's the idea. Anyway, so it is scheduled to come out in September of this year. There's already an Amazon page if you want to go check it out. The cover is not available yet, but the book is there. You could pre-order it. We encourage people to pre-order the books. That always gets people excited, bookstores, etc. So anyway, what I was saying was I handed in the manuscript early December. My editor read it, got comments back to me late December. I've made revisions on it and handed those in, and I handed those in just a couple days ago. That's why this AMA is getting to you a little bit later than I would like, because I've been working on edits for the book. And it's very exciting. Like, sometimes when you're explaining something and you think you got it right and it's understandable, it's a really, really good feeling. Other times I'm like, are they really going to understand raising and lowering indices? This is this is weird. This is a little bit of abstraction that you don't usually get in typical physics books. But I think that, just knowing what derivatives are, what partial derivatives are, which you need to get to Hamiltonian mechanics, it really changes your views on life. And I want to share it more widely. So even if the physics in this series of books is hit or miss, hopefully you will appreciate the mathematical language and concepts that are used there, especially if you're not a professional physicist. Hopefully it will be useful. That's the idea. Anyway, I just wanted to get that off my chest to explain to you why this AMA is a couple days late. And I think that's all I wanted to say about that. So for those of you who don't know, for those of you who are new to this whole process, these Ask Me Anything episodes happen 11 times a year, every month other than January. And the questions are asked by Patreon supporters of Mindscape. So you can go to patreon.com/Sean M. Carroll if you want to become a Patreon supporter. If you do become a Patreon supporter, you get ad-free versions of the regular podcasts, plus you get to ask questions here at the AMAs. I don't get to answer everyone's question. Sorry about that. They're all usually good, but sometimes I just don't have anything interesting to say. That's usually why I leave the question out. I'm just not inspired to say anything interesting about that. And I don't want to waste people's time by reading a question and saying, no, I don't have anything interesting to say about it, or insult the questioner. I'd rather just skip that question entirely. Feel free to try again the next month. I'm not guaranteeing that I will do it next month, but you can keep trying. There's no rule about trying again and again. Since it's been a couple of months since we've done it, I will try to go a little bit longer this time. I know I already go pretty long. I do have a tendency to do that, but we got to get some more questions in there. So let's stop wasting our time. Let's go. Rodrigo Nader says, I always tend to understand the emergence phenomenon as a consequence of pattern recognition. The cream coffee example shows that after mixing, many different combinations of particles look the same. A pattern emerges to us. Maybe an alien life form who recognizes completely different sorts of patterns would see different macroscopic states after mixing. Is emergence really a property of nature? Could you give some other examples to clarify that? So I think it's a very important question because I think a lot of people do have exactly the impression that you have, Rodrigo, but I think it's not correct. I would have to disagree with this. That is why Dan Dennett calls emergence real patterns. It's the word real there that really matters. It's not an observer-dependent phenomenon for a couple of reasons. One reason is that there aren't any aliens or any robots or anything like that that will see radically different things when they look at the cream and the coffee mixing together than we human beings do. It could be a little bit different if they're subject or if they're sensitive to different wavelengths of light or something like that. But it will always be the case that only, some tiny number of photons, relatively speaking, are carrying information from the cream and coffee to your eyeball. Way, way insufficient to give you access to the specific locations and velocities of all the molecules of cream and coffee. So there's a physical fact about what is observably accessible to you that points us in the direction of coarse graining the system in a certain way. The other thing, which is even way more important, I would say, or also very important, is that the information you do get is useful. It's the information you need, even though it is coarse-grained, to say something about what will happen next. So, in other words, the best example ever of emergence is the relationship between kinetic theory of atoms and molecules and fluid mechanics, or gas mechanics, if you want, right? You can take a box of gas, you can describe it in terms of atoms, or you can describe it in terms of a fluid, and that's an emergence phenomenon. The fluid description is completely different. Its ontology is different, right? It says there's a fluid in the box, as opposed to the atomic description that says there's a collection of particles in the box. And there is a perfectly well-known map from the set of configurations in the atomic description to a set of configurations in the fluid description. You can coarse grain very, very literally. That's not always possible, but in the box of gas, it is. And finally, the information that you're left with by that coarse graining, namely, let's say you pick some coarse graining size, cubic millimeter or whatever. In every cubic millimeter of the box, you have a temperature, a density, pressure, things like that. And that information is enough to predict how the gas will behave to very, very good accuracy. That's what you do when you model the climate or the atmosphere, right? Or when you're modeling jet exhaust or anything like that. You're doing fluid mechanics, even though you know it's really atoms underneath. And that is an objectively true fact, that even though you have a tiny, tiny fraction of all the microscopic information in the system, it is still enough to make interesting predictions. If you took random subsets of the information, you would not be able to use that to make interesting predictions, but the particular information you get from that coarse graining operation does give you enough information to make predictions. That's a crucial aspect of emergence. I don't think we have the once and for all theory of everything as far as emergence is concerned, a theory of emergence everything. But I think these two aspects are both crucial and non-generic. You wouldn't expect necessarily that you could observe a certain subset of the information of the system and have that information be enough to predict what's going to happen next in general, if you just had random things you could observe. But in the real world, we see it again and again. So that's a very deep feature of the real world that I think calls out for some kind of explanation. Rob Greiber says, I've been listening to early episodes of the podcast and really enjoyed your conversation with Cornel West. My question for you relates to one of Professor West's closing comments. You ask him, what is it that unsettles you? I won't quote his answer entirely, but he starts with, well, it's what hangs in my closet and is one of the themes of my writings really for the last 30 years, which is nihilism. And it comes in different forms. There's secular forms of it. There's religious forms. He goes on to link the idea of nihilism today to the disconnectedness of the late modern world. It's all about posing, posturing, spectacle image, trying to manipulate in order to pursue our careers, our next opportunity. I'd be curious to hear what you thought of that exchange, but more I'd like to put that question to you. In these strange pre-post-pandemic times, as politics and social media pull apart, even as science and innovation blows forward, what unsettles you and what gives you hope? This is a great question. It's a very thoughtful question. I'm sure I'm not going to be able to do justice to it. It's not something I've really thought carefully about, but I can give you my immediate impressions. I get the fretting about nihilism. Nihilism just being, a conviction that everything is meaningless, right? Nothing really matters, etc. This is part of why I wrote The Big Picture, to establish you don't need to be nihilist even if you're a naturalist. I guess I would worry a little bit, or I would wonder, let's put it that way, how accurate the worry is that nihilism is something connected to the modern world specifically. Like there's more nihilism now than there was before. I guess it depends on what you mean by nihilism. I mean, there is a sort of disenchantment in our view of the world. We used to have a picture of the world that was much more convinced that there were spirits and purposes and natures out there in the world, and those have gone away. But there never were such spirits or purposes. So that was wrong, and I'm glad to be correct. I'm glad to have improved our understanding of the world. I don't consider that to be a loss. And I consider that the real purposes and meanings that are there in the world come from human beings, just as they always did. So I would have to see like a careful, scholarly investigation into this question of, has nihilism become more of a problem in the modern world than it was? Or if it is more of a problem, is it a worse problem than what it has replaced? Let's put it that way. Your harder question is, what is it that unsettles me? That's what I was hoping no one would ask. But look, I'm not going to say anything original or new. I talk about the things that unsettle me all the time. I guess if I have to pick one, it's the gradual disintegration of our ability to act like a democracy. And I know that people are going to say that we never really were a democracy, et cetera. Fine. Okay. I mean, democracy in the United States and elsewhere in the world has always been sub-ideal. It's always fallen short of what you might want it to be. It's still better, in my mind, than any of the alternatives. And I'm extraordinarily worried that it's not going to last much longer. We know it doesn't always last. Democracy sort of appears and disappears historically, and there's no reason to think that we should necessarily be different. And I also think it's perfectly obvious that here in the United States, if you have like Republicans and Democrats, one side is far and away more responsible for the threats to democracy, namely the Republicans, in case you're wondering, than the Democrats are. But I absolutely think that all sides are falling short in worrisome ways, okay? In the following sense, that if you think that democracy is good, if you want it to work, if you want it to be a success, you have to be committed to the ideal of working with people with whom you disagree. And that's the ideal that I think is just disappearing on both sides. It will always be true that some people with whom you disagree with them so strongly that they're not in any sense partners. They are just the enemy, right? You can only fight them. You're not trying to work with them. But if that's most other people, or if that's half the country, then you don't have a functioning democracy, and you won't. If you consider half the country to be your enemy, then there's no way for democracy to work under those circumstances. And I'm worried that more and more people think that way on both sides. If you're pro-democracy, the question you should be asking yourself is, how far can someone go to be on the other side, be on the side I disagree with, and yet I will still work with them? Right. And this is not an easy question. I'm not trying to simplify it. We can always remember the podcast with Teen Nguyen where he warns you against oversimplifying, looking for false clarity in these complicated social situations. It's not simple to say these people are not worth engaging with and these people are. But the point I'm making is you have to be able to engage with people who you don't like, who you don't agree with, but nevertheless, they're your fellow citizens and you have to work with them somehow. And that's becoming increasingly harder. You don't make peace treaties with your friends. You make peace treaties with your enemies. That's my biggest worry. That's what unsettles me, that in many ways, people don't want to talk to each other. They don't want to understand each other. They don't want to agree to disagree. They just want to fight. And they just want to, have a quote unquote democracy by assuming that their views should be the ones everyone votes for. Now, of course, it's also okay in the context of democracy to work to change people's minds. That's crucially important. That's a very high priority thing to do. So it's not only that you have to work with people you disagree with, but you have to try to convince them to agree with you. But that second thing, convincing them to agree with you, won't always work. There are people with fundamentally different values, and we have to be devoted to finding a way to live together. I'm not so sure we are devoted that way. I'm not even so sure that we try to attain that goal anymore. That kind of unsettles me. You also ask what gives me hope. What gives me hope, let me give you a very silly answer and self-serving answer. What gives me hope is that so many people listen to podcasts like this. And not just because it's my podcast. What gives me hope is that I do find empirically that when you give people good ideas, good information, thoughtful things to chew over, they are surprisingly interested in tackling big ideas. I think that people like to say that other people are just stupid and they just want to watch reality shows or whatever. And sometimes they do. I don't even mind watching a reality show in the right place, right time. What is it? MasterChef Junior. Come on. This is genius. I would always watch MasterChef Junior. But it can't be everything that you do. And I think that we underestimate the public sometimes in terms of intellectual engagement. That's one of the reasons why I'm writing the book, right? The Biggest Ideas books, I'm trying to provide, it's not going to be, number one bestseller, given what is inside the book, but I think that there are more people than we usually think who are willing to dig into equations and learn some physics. Likewise, I think there are more people than we usually think who are willing to think hard about philosophy or politics or economics or the climate or whatever. That's what gives me hope, is that when we give people the chance to engage with ideas in thoughtful ways, more than you might guess, they leap at the chance. All right, Bruno Teixeira says, I don't understand what you mean by maybe dark energy is just the cosmological constant, especially when opposed to other hypotheses related to quantum fields. Isn't GR a classical emergent description of a fundamentally quantum phenomenon? When we figure out quantum gravity, won't dark energy be something in that model? Well, I mean, maybe, sure. I don't know what quantum gravity is yet, so that's hard to predict exactly what's going to happen. But that is completely compatible with dark energy being the cosmological constant. Like you just said, GR is a classical emergent description of a fundamentally quantum phenomenon. But emergent descriptions can be correct. General relativity is a very, very good fit for what happens in cosmology. So when I say dark energy is just the cosmological constant, I mean at the level of emergent description, where we're describing the universe as a curved space-time, obeying the rules of general relativity, I think the vacuum energy, the dark energy, is going to be a cosmological constant rather than a modification of Einstein's equation or some dynamical thing or something like that. What the question you're asking is, how do we explain that value of the emergent cosmological constant at some deeper quantum level? That I don't know. I would love to know that. If I knew that, I'd be writing a paper on that. Don't have any good ideas right now. Paul Torek says, Joshua Green claimed that when we use slow, careful moral thought processes rather than quick gut reactions, we'll get utilitarian conclusions. Thus, ethics gets simplified to a single dimension of happiness. But does that preference for simple theories only make sense when one views morality as a Platonic realm out there, independent of human concerns? How plausible is it to you, as a moral constructivist, that morality would be so vastly simpler than the human beings who construct it? Well, I think there's a couple of parts of that question that I would take. I would worry that are not quite an accurate description. I don't think that if you ask Josh Green what he meant by utilitarianism, he would say ethics gets simplified to a single dimension of happiness. I think he would say it's much more nuanced than that. Now, it is true that utilitarianism is based on the idea there is something called utility that we try to maximize. But by itself, that statement, there's a number called utility we try to maximize, is almost content-free. Because if you have any rules for any process of making a decision, right? Should I go left or right? Should I, save this person from drowning or save myself? Whatever, should I, push the lever on the trolley problem? Any decision-making algorithm can always mathematically be cast as maximizing some number. And then you can call that utility, right? So it's almost an empty statement to say you should maximize some number called utility until you tell people what the utility is. And it's true that back in the early days of utilitarianism, it was thought to be happiness or something like that. But more modern, sophisticated approaches to utilitarianism, or even going back to John Stuart Mill, they had more sophisticated approaches for what was meant by utility. Now, one of the reasons why I'm skeptical of utilitarianism myself is because even though you can be more sophisticated in defining utility, you're still imagining, in practice, in utilitarian practice, you're still imagining that there is some quantity that you can add up over different people, right? So this person has a certain utility, that person has a certain utility, et cetera. This action has a certain utility. You just add them up and maximize that. So it's a little bit more specific than just saying you're maximizing something. There's some procedure finding this thing that you're maximizing. That's what I'm a little bit skeptical about, whether that there's some quantity that I can compare one person's utility to another person's utility in a way that I could add them together, in some linear fashion. That worries me about that particular step. But one of the points that Josh made, which I thought was an interesting and important one, is that in these more sophisticated versions of utilitarianism, it can almost seem like virtue ethics or deontology or something like that, depending on where you get your utility from. Maybe you get your utility from following rules. If you literally said that all of my utility comes from following these rules and not breaking them, then you're both a utilitarian and a deontological moral person at the same time, right? So that sense is that utilitarianism is pretty flexible. And you can imagine a lot of different versions of it. So on the one hand, that makes me more sympathetic to the idea that it might work. On the other hand, it makes it much more loosey-goosey and maybe less useful because we haven't pinned down exactly what we mean by utility. So anyway, my answer to your question is I don't think it's necessarily true that utilitarian morality is so vastly simple as you make it out to be. That's not to say that I think it's a useful way of thinking about things, but it's potentially useful. Let's put it that way. I think that I would grant them that. Paul Briddick says, The determinist approach proposes that all behavior has a cause and is thus predictable, and therefore free will is an illusion. A theoretical supercomputer is programmed to account for all particle behavior in the vein of Laplace's demon and predict the future of all behaviors going forward in the universe. If this computer predicts you will drink coffee for breakfast tomorrow, are you powerless to switch to tea? So there's a whole bunch of things going on here, packed into a small package. So let me unpack a little bit. Determinism is probably not right as an operational question for our universe. First off, right? There is quantum mechanics. We have no clue whatsoever. In fact, we have very strong evidence that it's not possible to have a complete quantum state description of the universe and deterministically predict what will happen next, what will be observed next. All of the indications that you can't do that. There's some intrinsic randomness there. Now, some of us, like myself, believe that there is a deeper explanation that involves not just the world we observe, but other worlds also. And the quantum state of the whole picture is deterministic. But that doesn't help you make predictions for what's going to happen next. And it's still implausible in practice. Other people who I don't agree with, but they're out there, some of my best friends, think there's only one world, but there's some hidden way that there is information that does deterministically predict what will happen next. But even those people will be very quick to say, you don't know and never will know what that information is. So to grant you the question, we have to imagine that there is a version of quantum mechanics that really is deterministic, and that you're telling your theoretical supercomputer information about the universe that no human being will ever be able to know. Okay, so let's say that. And furthermore, we have to imagine that your theoretical supercomputer is not within the universe. There are problems with self-reference. Janae Ismail just wrote a very interesting article in Eon, I think, online that you can read about this, that there are sort of problems in practice, in principle, I should say, with imagining a perfect predictor within the universe that tries to predict the universe that it's within, because it has to predict itself. And there are sort of loops and paradoxes that it gets into. So again, to make sense of your question, we have to imagine that not only are there deterministic laws that are known to the computer, but the computer itself is outside our universe for whatever reason. But if we grant you all that, then yes, I am powerless to switch to tea. That would be my answer. Varun Narasimhashar says, thank you for your illuminating conversation with David Reich. It touched upon Indo-European history, and my question is about that. Are lay people in America and elsewhere aware of the current cultural movement of Hindu nationalism? It is advertised as a revival of bygone glory, but in reality, I find it to be rife with jingoism, exclusionism, and a flagrant historical revisionism that flies in the face of the academic consensus on archaeology, genetics, etc. I worry for India, and I believe the entire civilized world should worry about such a counterproductive phenomenon taking hold of a globally important democracy. It's a good question. I'm not really familiar at a data-driven, evidence-based level with how familiar Americans are with these different questions. My suspicion is that they've heard of Hindu nationalism in India and they don't like it. You know, we have our own nationalism here. People wear these red hats saying, make America great again and keep the immigrants out, right? And we think, some of us think that our nationalism is terrible. Others are all for it. But it's much easier to be horrified at other countries' nationalism, right? Even if you think your own country's nationalism is pretty awesome. So I don't think that many Americans are in favor of a resurgence of Hindu nationalism in India. We think that other countries should be, open and cosmopolitan and get along with all different sorts of cultures within their societies, even if we have trouble living up to that. So, I agree. I don't have anything wise to say about this. I think that India is a crucially important country for the world. I think that, it has a sort of mixed history with democracy. It is a democracy, but not always a perfect one. Again, you could say the same thing about the U.S. It is not, as wealthy as the U.S. or some European countries. And, there's every reason to think that it kind of should be in some global sense. So you can imagine there's very understandable frustration for why it's not. And when you're in situations like that, where you don't think that your economy or your living conditions or your global power is as elevated as it should be, you take out your frustrations in the wrong directions. And nationalism and populism are very common bad places for that to go. So I don't have any wisdom specific to India, but I can absolutely see the similarities between what's happening there and what's happening to other places in the world. Preston Justice says, I've just finished Stephen Pinker's new book, Rationality, What It Is, Why It Seems Scarce, and Why It Matters. What are your thoughts on the arduous task of being more rational amidst the constant storm of cognitive biases with which we each must contend? More precisely, how can the average Josephine pragmatically increase their rationality points to avoid the illogical and sometimes deadly acceptance of quackery and flapdoodle that perpetually surrounds us? These are all good questions. These are constant questions. They're not going away. We can all strive to be better at this. I know I work to try to be better at this. We have had discussions here on Mindscape about precisely these questions. Maybe most recently with Julia Galef, who wrote a book on it, on the Scout mindset. I like Julia's book in particular because it is exactly addressed to this question of how I can be more rational rather than why aren't other people more rational, which is, that's a very common book that people write a lot of the time. But where I sort of get off the train a little bit here is near the end of your question, where you're talking about quackery and flapdoodle. Flopdoodle. I don't know if I've heard that one. I think it's flapdoodle. Anyway, nobody intentionally accepts quackery and flapdoodle, right? They all think that they're being rational, and there's sort of a level of irrationality that we usually associate with words like quackery and flapdoodle that is so irrational that if you're spending your time worrying about your cognitive biases, you're probably not susceptible to that particular brand of quackery and flapdoodle. But there are other kinds of irrationality that you can be susceptible to, even though you know that astrology is not correct or Bigfoot doesn't exist or whatever. There are ways of justifying your choices, your attitude towards other people that are deep down just as irrational, but don't have like the big shining neon light saying this is quackery on them. I have no short and simple rules for doing that. One warning sign is if people say, cognitive biases sure are bad, I'm glad I don't have any, then that person is not being rational. If you think that you have no biases, that you're completely objective, that you have no tribal affiliations or identities, you're not being honest with yourself, right? Even if you think that you shouldn't, even if you think that you should work to minimize those aspects of how you think, you have to admit that they're there and stand up to them and recognize them rather than just deny their existence. So recognizing what our biases are is certainly one of the biggest steps. And one very obvious thing is what beliefs are in your best interests, right? What are the things that you believe are true, which just happen to flatter your own view of yourself or make yourself look good, right? Those are always the danger points. I don't want to get into specifics because every case is different, but read Julia's book or listen to that podcast. Herbert Berkowitz says, is CERN tourist friendly? I think pretty much it is, actually. CERN, the giant particle accelerator laboratory outside Geneva. In Geneva? Yeah, maybe it's part of it is in Geneva. I've visited several times CERN, but of course I visited there as a physicist. So I have not visited as a tourist. So I'm not quite sure how much there is to do. I know there are exhibits and things like that. There are absolutely public available places. But two things to note. Number one, you're not going to get to see a particle detector. They're not going to take you down beneath the ground to see Atlas or CMS or something like that because they're all sealed up or physicists are working on them. Actually, if you happen to be there while things are being renovated while it's downtime and the machine is opened up, then maybe you could, but I still don't think that's a kind of public available thing. What there are exhibits, almost like museum kinds of exhibits. The other thing is that to the working physicist, CERN is a bunch of offices, right? And when I'm at CERN visiting the theory group, it's not a place that any tourist would want to see. It doesn't look any different than visiting Caltech or whatever. But again, there are, public-facing sides of it. So if you happen to be in the area, I wouldn't visit Geneva just to visit CERN. But if you're in Geneva, in between looking at the watch factories and the banks and so forth and the lake, a visit to CERN would be a lot of fun. Okay, I'm going to group two questions together here, which we sometimes do. One is from Kathy Seeger, who says, what actually happens during entanglement? As it is no classical interaction of any kind, how can it best be described? Is it the same kind of process for particles / massless particles and local / non-local, or are there different types of entanglement? And then George Robinson asks, what principle determines how and when quantum states become entangled? I read sometimes particles get entangled, sometimes they don't, but what is the theory of wave functions that says when and why the entanglement necessarily happens? I worry that for both these questions, which are both basically asking how does entanglement happen, I'm not going to give a very satisfying question or answer here because, I don't know, there's nothing... Entanglement is kind of the natural state, right? So the point of quantum mechanics is that unlike classical mechanics where you say I have a bunch of particles, every particle has a position, every particle has a momentum. In quantum mechanics, you say I have a bunch of particles, every particle has a possible position that it could have, right? It could have a position that I could possibly measure it to be in. And the wave function assigns a number, a complex number, to every possible configuration of all the particles. So nowhere in quantum mechanics is there the idea that an individual particle should have its own separate wave function, right? There's just a wave function for the whole collection. It's a very, very special case where you have one particle where the wave function for all the particles takes the form, the wave function for one particle times the wave function for all the others. Sometimes that happens, but that's kind of very special. If you think about all the different ways that the big wave function could depend on all the variables, that's a very specific, special way. And that's the case where that first particle is unentangled with the rest of the particles. So entanglement is by all means the generic case in the space of all possible quantum goings-on. That's hidden from us, that feature of quantum mechanics is hidden from us in some sense because we live in a world which is big and macroscopic, and the things that we can observe are sort of deep into the classical regime where for all intents and purposes, the entanglement is negligible, okay? We don't see things carefully enough to notice that they're entangled with other things. You wouldn't notice by looking at one, but you could do complicated experiments looking at many and after the fact, infer that there was some entanglement there. So having said all that, when do things become entangled? Most of the time is the answer. At the quantum level, most of the time. If I have two electrons and I scatter them, right? So two electrons will repel each other by the electromagnetic force. If they were classical point particles, you would find out exactly what their positions were, exactly what their velocities were, and predict exactly how they would scatter. Since they're not, there is a wave function for both the particles, a function of both their positions, okay, let's say, and I can start them off as little wave packets. I can't localize the individual electrons perfectly, but they can be almost localized. They can be like a bump in one area of space, and the two bumps are heading toward each other. But then what you predict when they scatter is not some definite angle at which they scatter, but the wave function for the two of them becomes entangled. And there is sort of a probability that one particle goes off in one direction and the other goes off the other, and the same thing is true for all the other directions. So instantly, just from two charged particles bumping into each other, entanglement has occurred. Or if one particle, all by itself, like the Higgs boson, let's say or for that matter, a pion, a Higgs boson or a neutral pion, are both cases of single particles. So there's no entanglement that you're talking about. You just have one particle, nothing for it to entangle with, but it decays. Okay, both a photon, a pion, and a Higgs boson can decay into two photons moving off back to back. What direction are they moving off in? I mean, there's no way to pick a special direction because they're just single spinless particles sitting there. The answer is they move off in every possible direction, the two photons that are created, and they're entangled with each other. So you don't know which direction either one photon is moving off in, but you know that if one photon is moving in one direction, the other's moving in the opposite direction because the overall momentum is conserved. So the short answer is entanglement happens all the time. The more difficult question, which I'm glad you didn't ask, is why do things look unentangled to we big macroscopic observers? But that has to do with the classical limit and so forth and so on. I hope that's shedding some light on the question. Frederick Axthorne says, enough with the physics already. Good, I'm with you, Frederick. Me and my friends are coming over from Sweden this summer to stay at the Aria in Vegas for 2 weeks. Would love to hear your general thoughts on playing poker in Vegas, dining, and general entertainment. Well, I have many thoughts, most of which are be willing to spend money. It makes your visit to Vegas a lot more fun if you're willing to spend money. You don't expect to make money. Maybe you'll make money. I don't know. I mean, I don't make money going to Vegas. Maybe Liv Bory, our previous guest, or Maria Konnikova could make money in Vegas, but I tend to lose it. I think that like once or twice I've had a trip to Vegas and I've made enough money playing poker to pay for the hotel room there. I don't think I've ever made enough to pay for the hotel room and for the dinners. With Jennifer and I going to Vegas, eating out is a huge reason why we go. Like we can sort of kick back during the day, relax. You can go to the pool or sit and read a book or whatever, or just kick around. And then have some of the world's best food at night. The Aria is a great place for food, but, you know, explore all the different possibilities. The MGM Grand across the street has a bunch of good places. It has the Atelier Joel Robuchon, which is a wonderful semi-casual version of haute cuisine there. The Bellagio and Caesar's Palace have amazing high-end restaurants like Picasso and Guy Savoy, but there's also a lot more non-high-end restaurants that are really excellent. Roy Choi, who is the chef who is in charge of the Koji barbecue taco truck here in LA, opened a Vegas restaurant called Best Friend, which I highly recommend. It's in the Park MGM, a weird, wonderful collection of, you know, Korean/Italian/barbecue food that will leave you smiling for sure. The Cosmopolitan also has a lot of fun little restaurants. There's a Jose Andres Spanish restaurant that is really, really good. It just goes on. There's just so many good places to eat. Also window shopping or real shopping if you're into that. But Aria has some shops. It's not great. Aria, I think, made a terrible mistake. That whole city center complex that Aria is part of, rather than having interesting shopping, they just built like a high-end mall, the Crystals Mall, right in the middle of the complex. And it has, you know, Prada and Gucci and whatever, if that's what you're into, but you can get those other places. Places like the Forum Shops at Caesar's Palace have quirky little shops that are not located anywhere else. So I would give that a look if you want. For playing poker, you know, I haven't played poker in Vegas in quite a long time because there's been a pandemic. The Aria has a great poker room. It's a little bit high end, so you know, be ready for that. MGM Grand is a slightly lower end, so a little bit cheaper, a little bit weaker competition if you want to try that out. Also, it's still a very luxurious environment overall. And then the Bellagio is always fun to go to, just so you can say you went to the Bellagio. I actually tend to do way better in the tournaments. They have like daily tournaments at almost every poker room in Vegas. $100, $150. You enter. Maybe 30 or 40 people have entered, that kind of thing. You know, you start in the morning and in the evening, one day. But you can also just play ongoing ring games at a table anytime. So it's a lot of fun. You meet crazy people. You meet a whole wide variety of people. You're playing poker and the person on one side of you is, you know, wearing shorts and a t-shirt, and the other one is wearing a tuxedo on the other side of you. And great stories bouncing back and forth between all these people coming in from all over the world to play poker in Vegas. So I hope you have a good time. Emmett Francis says, do you have any advice for a PhD student, me, working on putting together some disparate pieces of work into a dissertation? My temptation is to spend time working on telling a coherent story through the dissertation, but my impression is that not many folks read the dissertation itself, and I should perhaps focus more on getting at least some of my unpublished research submitted to a journal before I graduate. Thoughts? So I think that this might be one of those things that depends wildly on what exact subfield you're in. So in theoretical high-energy physics, it's a very simple thing. No, don't spend any time whatsoever telling a coherent story. Most places, like at Caltech, for example, or at Harvard, where I was, you just staple together your papers, write an introduction, and whether or not you want to spend a lot of time with the introduction, that's up to you. It doesn't matter if your papers are co-authored with other people, as long as you just are honest about, who the co-authors were and give them credit. And as long as a substantial amount of the work was done by you, they're totally acceptable for chapters in a thesis. I've had students who've collaborated with me on papers, more than one student, and a single paper appeared in more than one PhD thesis defense as a chapter. As long as you're honest about what you did there and really contributed to it. And I get where you're coming from, because a lot of people, the PhD thesis is a big thing. Okay, I think a lot of people make the mistake of, by the time they're defending their thesis or whatever, it's anticlimactic, because there's a lot of pressure to get a postdoc job, to figure out the rest of your life and things like that. And if your advisor is even halfway competent, you should not get to the point of defending your thesis without it being a foregone conclusion that you will pass. It should not be a stressful thing. It can be stressful, but it shouldn't be. And therefore, for a lot of people, they're like, okay, they're ready to move on. And they're like, just give me the degree and I move on. Whereas I think it's a big deal. You worked hard for years to get to this point. And I'm a big believer in, pomp and ceremony about these things. That's why I recently posted on Twitter the updated collection of champagne bottles in my office, one for each successful PhD thesis defense. Whenever one of my students defends a PhD thesis, I buy 2 bottles of champagne. One goes to me, one goes to them, to do with what we want. We drink it, but then we store the bottle or not as we choose. So I'm a big believer in caring about the PhD thesis and its defense, but as a text, as a collection of words and thoughts, almost no one's going to read it, right? Especially if it's like in theoretical high energy theory, it's a collection of papers. You could write an introduction that is pedagogical and has some value added, but rewriting the chapters so that they fit together to tell a story for something that no one will ever read is probably not the best use of your time. If you could get some of the unpublished research submitted to a journal, that would be much more useful. Yes, I agree on that. On the other hand, there are other subfields that think about it very differently in different ways. When I was at Chicago, they had what I thought was a very weird rule, which is that PhD students, you acted like a regular PhD student. You wrote a bunch of papers, collaborated with your advisor, with other students, with whoever. But then your thesis was one hefty single author paper. You had to write a paper and it had to be submitted to a journal and either published or on the road to being published. And that was your PhD thesis. I thought it was a dumb rule. I get it. I get why they want to do it, because you're supposed to show that you can do it all by yourself. Good. But it's just not natural. I think that a lot of things at Chicago were rules, or even grad schools more broadly. There are a lot of rules that people come up with, hurdles you have to leap to successfully get through this process that are not necessarily aimed at making you the best researcher you can be. A real researcher will write a single author paper when they have a good idea by themselves and have the wherewithal to write it up themselves. That's fine. But sometimes that doesn't happen. If I have a good idea and I need someone to do some 3D numerical simulation, I'm not going to either not do it or try to teach myself 3D numerical simulations. I'm going to go to a friend who can do 3D numerical simulations and we're going to collaborate. And that's the natural thing to do. And I think it's weird to sort of penalize that in some way. Anyway, so that's a different way of doing it. And my point is just that different places, different subfields have different ways of doing it. So you should really ask this question of people who are exactly within your subspecialty, just so I'm not leading you the wrong way. Jan Smith says, how do you keep yourself in good physical shape? Well, a question is being begged here, whether or not I do keep myself in good physical shape. But to be honest, I actually, for the past few years, have been a member of a gym and signed up for personal training classes at the gym. And the reason I do that is because otherwise I just don't work out. I'm a big believer in working out, exercising, trying to stay relatively fit, not like athlete level toned or anything like that, but moving. Like I have a job that basically involves sitting in front of a computer screen all day, right? Or sitting in front of a piece of paper. Although these days I use my iPad, so sitting in front of an iPad, which is not any much better. A lot of sitting is involved in my job. Even right now when I'm podcasting, I'm still sitting, talking to you. So getting out and moving around is I think something I think crucially important. And even though the personal trainer is good because they make sure I'm doing exercises correctly and the right collection of them, the single biggest thing is that it's an appointment and I got to go, right? I can't just say, I don't feel like it today. And I completely understand this is only because I'm at a point in my life now where I can afford something like that. It gets me out of the house. It's worth the money, I think, right? And it definitely does make a difference since I've started doing it. Jennifer, who is a workout demon, she's naturally like she works out every day and has for many years. She has a black belt in jiu-jitsu, and bless her heart, she never sort of nudged me to do it, even though when she first met me, I was not working out very much at all. When I was like a student, when I was in grad school or postdoc, I would like play basketball all the time and run around and do things. And then you kind of like get a little sluggy after that. But even though she was completely silent about the matter, her good example nudged me to doing something about it and getting out there and going to the gym. So that's what I try to do. Okay, I'm going to group two questions together. One is from Andre Dinu, who says, you mentioned in the past that Hilbert space, which for those non-experts out there, the space of all possible quantum mechanical wave functions. Hilbert space could be either infinite dimensional or it could have a finite number of dimensions. But in the latter case, the number of dimensions could be at least 10 to the 10 to the 120. How is this number estimated? Is it approximately 3 times n, where n is the number of elementary particles in the visible universe? Something like that? The other question is Qubit, who says, I often think about what kind of mathematical object the wave function of the universe really is. To keep things simple, I like to think about it in the position representation. My first guess is that the wave function is then a function of n location vectors, where n is the number of elementary particles in the universe. However, I'm not sure how this picture can handle the creation and annihilation of elementary particles. Should I think about this like the wave function gets or loses some of its arguments during the time evolution? Not sure how the Hamiltonian of the universe could achieve such changes to the wave function. So these are not exactly the same question, certainly not the same question, but they're related to this issue of Hilbert space and the number of dimensions of Hilbert space and what the wave function really is. Let me say one thing, which I usually resist trying to say, but it still remains true, which is that I wrote a book about this, Something Deeply Hidden. And if you're really interested, if you're interested enough to ask these kinds of questions, you should read the book, because I do answer these questions in the book. Now, admittedly, I own books and have even read books and nevertheless do not understand or remember everything in them. So if you've read the book and still have questions, that's completely cool. But you'll get a much clearer picture, not just of the answer to an individual question, but of how everything fits together if you check out the book. Okay, more than I can say in an AMA answer. So the point is, when you start with a quantum mechanical system thought about as some collection of particles, as soon as you just say, well, I have a particle in space, okay, so the particle can take on any location. In ordinary classical mechanics, space is continuous. The particle can be anywhere. The Hilbert space that you get from that, even from one particle, is infinite dimensional, because the dimensionality of Hilbert space is the number of possible observational outcomes when you measure something about the particle. So if you measure the position of the particle and you could get an infinite number of different answers, that's an infinite dimensional Hilbert space right there. So when you say that the universe might have a finite dimensional Hilbert space, you've already said there is something that is not just taking a bunch of particles and quantizing it. You're doing something more elaborate. Now, let me skip ahead a little bit to Qubit's question about how particles could be created or destroyed. If you have a theory of n particles in quantum mechanics, or for that matter in classical mechanics, and that's what your theory is of, then in classical mechanics you would have a phase space, in quantum mechanics you have a Hilbert space, and there's no way for the number of particles to change. This is why you invent field theory. This is exactly the reason. You could start with field theory and find out that it looks like particles. You can also start with particles and say, rather than having n particles, my configuration quantum mechanically is a superposition of 0 particles, 1 particle, 2 particle, 3 particles, and there can be transitions between them. Okay, but they're all there. They're all there in the possible places in Hilbert space. So you have to add up all those things. And what you find mathematically is that it's completely equivalent to a quantum field theory. Even if you just start with particles, a many-body quantum system, as they call it, is equivalent to a quantum field theory. And it's the quantum field theory that lets you talk about transitions between different numbers of particles, creation, annihilation. The wave, the quantum field is waving or it's not. So it's very easy to understand creation, annihilation of particles in the field theory perspective. The Hilbert space never changes size. In fact, it's always infinite dimensional, so it becomes a little bit less puzzling. But it doesn't even sort of get a bigger infinity or a smaller infinity. It just always includes the possibility of 0 particles, 1 particle, 2 particle, up to billions of particles baked in from the start into Hilbert space. Parenthetically, by the way, the number of observable particles in the observable universe is something like 10 to the 88th. So it is not 10 to the 120. It's certainly not 10 to the 10 to the 120. So back to Andre's question then, where does this finite but big number come from if it has nothing to do with the number of particles in the universe? The answer is gravity. Remember that Stephen Hawking gave us a formula for the entropy of a black hole. Namely, the entropy is the area of its event horizon divided by 4 in Planck units. And we think that not only is that entropy a reflection of the entanglement between things inside, degrees of freedom inside the black hole and outside, but we also think that the black hole is a maximum entropy state. For a fixed volume of space-time, there's no configuration that is higher entropy than a black hole. And what that means is the fact that the entanglement entropy of the black hole is finite indicates there's a finite dimensional Hilbert space of things that can go on inside the black hole. And if you go through the math, it turns out to be e to the entropy or 10 to the entropy. The entropy is so big it doesn't matter whether you're raising it to the power of e or 10, honestly. And something very similar to that, you say, well, we don't live in a black hole in the universe. That's true. But we live in a universe that is approaching de Sitter space. De Sitter space is an accelerating universe with a cosmological constant, as we've already talked about. And de Sitter space is surrounded by a horizon, and it has an entropy. And the formula is the same. The formula is the area of the event horizon divided by 4 in Planck units. So it just turns out that if you run the numbers for our actual universe with a cosmological constant, if that's the thing that is causing the universe to accelerate, will approach a de Sitter phase with a horizon surrounding us. The horizon is the place past which, once a galaxy or something like that leaves, we can never communicate with it ever again. Space is expanding too fast for us to ever catch up to it. So there's a horizon around us, and its area is roughly 10 to the 120. So the entropy associated with that is 10 to the 120. The Hilbert space is 10 to the 10 to the 120 dimensional. It's a big number, but notice it has nothing to do with the number of particles. It's just a feature of space-time itself, which kind of makes sense. In the future, all the particles will more or less scatter to the 4 winds, right? That's what happens as the universe expands. In fact, I've told the story before, but for years, I was convinced, or at least speculated, that there was a family resemblance between the expansion of the universe and something called the cosmic no-hair theorem, which Bob Wald proved in the 80s, a theorem that says if you have a positive cosmological constant, you not only does the universe expand forever, but it always smooths out to become de Sitter space. And that always reminded me of the second law of thermodynamics, or of the process of equilibration in thermodynamics, where entropy increases until you get to the equilibrium point, and then you just stay there forever. It's equilibrated. So finally, Aidan Chatwin Davis and I proved a theorem under certain assumptions, which is necessary to do theorems. We proved a theorem that says, literally, that the second law of thermodynamics is the cosmic no-hair theorem. That if you assume you have a gravitational system whose entropy is proportional to the area of the event horizon, has a finite upper bound, you will evolve to de Sitter space, even without using Einstein's equation. So that was a very cool little result. Linus Larrabee asks a priority question. Remember, for those of you who are new, the priority questions, if you're a Patreon supporter and ask an AMA question, I can't always answer all of them. So the loophole is that every user Every supporter gets once in their life the ability to ask a priority question, which I will answer. I don't necessarily guarantee I will answer it to your satisfaction, but I will answer it up here. So Linus asks, on a 1 to 5 scale, how annoying are patrons who can't seem to follow simple directions regarding questions on AMAs? I know where you're coming from, because I do have, every single time I post the AMA, there are instructions, directions on, yeses and things to do and things not to do, yeses and nos for asking AMA questions. And every time people ignore them, but actually, not that much. Most people follow them. And there are a lot of directions. There are a lot of little rules, because we've been doing this for a while now. We know our way around. We know what the failure modes are. So honestly, it doesn't bother me that much. It's easy enough for me to ignore the people who do not follow the directions. Most common directions are keep your questions short. Most common directions that are ignored are keep your questions short. Don't ask me to read papers or videos or anything like that. I don't like special relativity puzzles. And everyone only gets one question per AMA. Those are the main, as far as I can recall right now, those are the main instructions. Every one of them gets violated every month. That's okay. I am more annoyed by other things in the world, honestly, right now. Lothian53 says, a many worlds question. This is probably too basic for this group, but how does many worlds explain the interference pattern observed with the double slit experiment? It would seem that the particles are interfering with the other worlds, but I thought that once split, there was no way that one world would affect any others. Well, yes and no. I would not say that the particles are interfering with other worlds, but other people would say differently. I'm not 100% sure about this, but I think that David Deutsch would say, oh yeah, they're definitely interfering with other worlds. But the point is that there is a set of worlds. Well, what can I say? There's a wave function, and it evolves according to Schrödinger's equation. That's what really happens, okay? Everything else is commentary, but the commentary is important. And in the commentary, we can talk about the world having branched by decoherence or not yet having branched. If the world has not yet branched, then you can talk about it either as just one world, and that's what I would honestly prefer to do. And in that world, there are wave functions for the different particles and things like that. Or even better, there's one wave function in that world for all the particles, all the stuff. Or you could sort of look into the future and say, there's going to be branching, so it's almost like there's a whole bunch of worlds that are already here, but they're all exactly the same. They're all identical, so it's as if there's just one world. And in that latter description, you would say that the particles passing through the double slits are interacting or interfering with particles from other worlds. But all the worlds are exactly the same, okay? So it's a weird way of talking in my perspective. I would just like to say, before there's any branching, before there's decoherence and the wave function is split, there's one world and there's a wave function, and the wave function is a wave and it interferes, and that's it. That's all you need to say. Don't think about particles. Think about the fact that it's a wave. It's the wave function that is the real thing. Okay, I'm going to group two questions together. Vladimir Belik says, imagine it's the last day of your well-deserved vacation, and after a fun and relaxing afternoon, it would soon be time to enjoy a special dinner with your wife. For this occasion, a magical personal chef is at your service. He can prepare any meal from your memory, but not only that, he can pick any location on Earth for this dinner, and he'll teleport both of you there, set the table, and shield you from any environmental effects if need be. What location do you choose, and what do you order? And then Trevor Britnell says, you recently mentioned that your favorite restaurant is Alinea. Have you been to any other 3 Michelin star restaurants or restaurants on the world's 50 best restaurants lists, and how do they compare? Let me answer the second one first, because it will illuminate the first one. Alinea is my favorite restaurant. Alinea is a 3 Michelin star restaurant in Chicago that I've been to a few times. And I have been, actually, to other 3 Michelin star restaurants. I'm not even going to be able to remember, I know I've been there, but I can't remember which ones are 1 star and 2 star and 3 star or whatever. But some fancy restaurants I've been to are the French Laundry, it's a famous one in Northern California. Vegas has several I've already mentioned earlier. Guy Savoy and Jules Robuchon and Picasso all have multiple Michelin stars. Dinner in London is one of our favorite restaurants. Dinner is the second best restaurant by Chef Heston Blumenthal. His best restaurant is the Fat Duck, which I have not been to. Fat Duck is up there in your list of possibly best restaurants in the world. Several restaurants in New York, Daniel and 11 Madison Park, and a couple of restaurants in Paris, Pierre Garnier, another Jules Robuchon, a couple in Copenhagen. I think Kong Hans Kelder was maybe 3 Michelin stars. Anyway, a bunch. I'm old. I've been around. I've traveled a lot, and I like eating. So I would rather spend my money on these restaurants than many other ways that I could spend money. Save your pennies. Actually, I've never made this point, but people think about spending a huge amount of money for a fancy dinner, because if you probably the upper limit would be at one of these restaurants. I mean, there's no upper limit because you can spend it on wine, right? You can get a bottle of wine for $10,000 and there you go. But if you just get a reasonable bottle of wine but otherwise, do the full tasting menu extravaganza, you should probably plan that per person you're spending a few $100s, maybe up to $500 at a restaurant like this. And that seems like just a crazy amount of money, right? $500 per person for a meal. But the way I think about it is it's a lot cheaper than going to Disneyland for several days, right? It's the comparison I use. Maybe I have said this out loud before, but I'm never going to stay overnight in the world's fanciest hotel room or drive the world's fanciest car or live in the world's fanciest house or whatever. But these meals at fancy restaurants are as good, arguably the best meals you can get in the world. No matter how rich you are, it's just as good as a meal that Jeff Bezos could possibly eat, right? And it's $500, which is, again, a vacation, right? So for me, that's well worth that particular way of budgeting your pleasure dollars. I'm a foodie in that sense. Anyway, to answer your question, Trevor, I think Linea is at the top of that list. Some of the meals I've had there have been better than others, but there's never been a dud. They've all been amazing. And it's Linea, for those of you who don't know, is one of these. They use the phrase molecular gastronomy, although I think that the chef Grant Achatz isn't a big fan of the term. By the way, I made an effort to get Grant Achatz on the podcast, and I think I came close. We were tweeting back and forth, but it never turned out. But Chef Achatz, if you're listening to this, we'd love to have you on Mindscape podcast. It's many small courses, right? It's not like a 3-course meal. It's like a 20-course meal or a 15-course meal, but the courses are very small and they're spread over 3 hours or whatever. But in every course, the reason why Linea is great is because I've been to bad molecular gastronomy restaurants where, they're trying too hard to be weird, There was one restaurant where, they bring a plate covered to your table, and then with a flourish, they open the plate and there's a cell phone on the plate. And then the cell phone rings and it says, come downstairs. And you go downstairs and you pick up your dish for that particular course. And I'm like, oh, yeah, this is kind of annoying. And there's foams and things like that sometimes, why is it like this? But Alinea manages to hit that sweet spot where every meal, every course is endlessly inventive and different, but just tastes really, really good. I mean, that's the thing. They have this real expertise at getting tastes together in ways that you wouldn't have guessed, and textures and timings and odors and sounds and the whole bit. It's the full experience that I really, really enjoy very, very well there. So that's, still my favorite restaurant compared to all those. I was a little bit disappointed with the French Laundry, to be honest. I think the French Laundry is phoning it in a little bit. Because I know that Grant Achatz has said that, if he gets a last meal, he would like it to be the French Laundry. And so I really wanted to go there to see what the fuss was about. I would say Linea is way better. So to Vladimir's question, that's what I would want. I want Grant Achatz to be my magical chef who prepares me a meal. The point is that when you go to one of these really good restaurants, not only is it really good, but you could never guess ahead of time what's coming next. The things they do with food are endlessly inventive. So I mean, I totally sympathize if someone says, I want a good medium rare steak, or, I want a good vegetarian souffle, or whatever it is you want. If you have a favorite thing and you want to get that, I get that. But I would put myself in the hands of someone who is much more creative and knowledgeable about food than I am, and let them do it. As to where, I thought about that. I really don't know. That's a good question. Could be somewhere weird, the top of Mount Everest, because you specified that there's a shield from any environmental effects. Or under the sea would also be a lot of fun. But I haven't really scouted these locations, so I couldn't tell you for sure. Tad Anderson says, physicists assume that fundamental particles of the same type are identical. How well do we know that? For example, how much variation in the mass of the electron would there have to be before it would upset current theories, or we could detect it with measurements? So if you accept the basic framework of current theories, the theory itself is pretty clear that all electrons have exactly the same mass. It is not an assumption. I mean, it's always a little bit wrong when you say, physicists assume this. That's just not quite getting your finger on the way physicists work. Physicists hypothesize things. They invent a theory, and according to the theory, something is true. But they're open to the possibility that it's not true. Physicists assume Lorentz invariance, but my first ever published paper was on violating Lorentz invariance, and it became very popular. Because if you can figure out a way to test deviations from those hypotheses, people are very happy. That's what they like to do. Variations of masses of particles certainly have been tested. I really don't know how accurately, to be honest. But what I wanted to emphasize was, as I just said a little bit ago, in modern physics, it's a field, right? There's an electron field that vibrates, and that we see it as electron particles. So this is why the masses of all electrons are exactly the same, because they're vibrations in exactly the same field. So this was, there's this story that John Wheeler was puzzled why electrons all have the same charge and the same mass. And he had this theory, when he realizes that an electron could be thought of going backward in time as a positron, that maybe there's only one electron. People are very excited by this, but that's not correct. He was not right. You have to understand, we've made progress since then. We know why all the electrons have the same mass and charge, because they're vibrations in the same field. We could definitely try to test it, and I'm sure we have, but I have no idea what the actual numerical limits are. Michael Shillingford asks a priority question. In the episode with Jody Azuni, it said that his object projectivism, which is tantamount to ontological nihilism, is bumping up against your work in quantum mechanics. But how so? The Dennettian ontology you contrast it with is obviously much more permissive. Is your physics research pulling toward the two poles of either eliminativism or permissivism? I'll apologize. I forget exactly what was said. What I can think of that I might have been getting at is the overall question of nominalism is something that has come up in my recent thinking about the foundations of quantum mechanics. And this is in part, again, I forget if I've mentioned this. Who knows what I've done and what I've not done on the podcast, but Justin Clark Doan, who is one of our previous guests, who writes about the philosophy of math as well as the moral philosophy. He and I had a podcast conversation, and we were also talking about mathematical realism, etc. And he has a set of arguments for mathematical realism. And in his mind, a good physicist is just going to be forced to be a mathematical realist because you need a lot of math to do physics. That's the simple, naive way of saying it. But also because once you have enough math, once you have sufficiently powerful mathematical formalisms, mathematical axiomatic systems, then as Gödel showed us, those systems can make statements about their own consistency. And if you want your physical theory to be consistent, which presumably you do, presumably you want the physical world to be consistent with itself. I'm not even sure how you could not have that. Then he says you sort of need to believe in the realism of those mathematical results. Okay, you can't prove the consistency of the theory within itself. You just have to assume it, and that's tantamount to mathematical realism. And I'm open to that possibility. I'm not an expert in these mathematical logic, foundations of mathematics questions, but it rubs me the wrong way a little bit. I want to think that the reality is the physical world, and mathematics is not part of that reality. It's a separate thing. It's a way we talk about the physical world. So that has led me to ask myself, is it possible to invent or to contemplate theories of physics that don't need sufficiently strong mathematics that they can even talk about their own consistency? They can just be consistent, or even better, just the right amount of power that they can prove their own consistency. There are versions of mathematical axiomatic systems that can do that. And so that's what I'm thinking about now. And I think the answer is yes. But again, I'm not an expert on it, so I'm not very good at it. So I can't tell you quite the answers. But I'm supposed to be writing a paper for a symposium that Justin is organizing. So we'll see how that goes, and I will let you know. So I don't think that I need so that it would be compatible with the kind of nominalism about math, right? Nominalism about abstract objects. You don't need to imagine that numbers are just as real as electrons are under that construal. Now, I think that's a little bit separate in my view from the question of levels of reality and emergent reality. Like I can think that I differ from Jody about the reality of Microsoft, for example. I think that Microsoft is real. I think it is part of a level of description of the world. It is not the most fundamental level, but it's as real as consciousness and tables and chairs are. Okay. Again, not an expert in this, but that's how I would put it. So I think you can be a realist about higher levels of reality, which is this Dennettian kind of sense of real patterns, and nevertheless not necessarily realistic about abstract mathematical objects. Chris Chotard says, I'm struggling with two different interpretations of the CMB anisotropy. The first one says that temperature fluctuations reflect the quantum fluctuations of the matter in its very early form. The second one says they are due to the gravitational lensing of all the matter the radiation has met during its journey to us. Could it be both? So no, it cannot be the second one. The CMB fluctuations are absolutely not due to gravitational lensing. There is an effect of gravitational lensing that contributes to the anisotropies of the CMB, but it's generally a very small amount, and it only shows up on relatively small angular scales. The vast majority of what you see when you look at CMB anisotropies is not from gravitational lensing. What it's from is density fluctuations of the primordial plasma just before recombination, just before the electrons and the protons teamed up to make hydrogen. Now, we speculate that those density fluctuations might be due to quantum fluctuations in the very, very, very early universe, but that's just a speculation. We don't know that. What we know with a high degree of confidence is that the temperature fluctuations 380,000 years after the Big Bang that we see in the CMB are from density fluctuations in the plasma at that time, not because of gravitational lensing since then. Francis Day asks a priority question. Often I hear you and your guest scientists use a phrase something like, I've thought a lot about this. In terms of thinking about a physics problem, what is your process? I would guess it involves talking to colleagues, reading papers, maybe sitting and thinking. Yeah, you have guessed exactly correctly. It involves all of those things. In fact, sitting and thinking is the most important one. I mean, talking to colleagues and reading papers is important. But if you're making progress on something that is new and interesting at a research level, you're doing a lot of lonely sitting and thinking. And then hopefully it works and you get to excitedly talk to your colleagues later. So, again, I'm always reluctant to label anything that I do as a process in any formal sense, because I just do whatever works in the moment and it's not necessarily very formalized. So different ideas, different things you've thought a lot about, come in different ways, come from different places. Some of them are kind of programmatic. So you say like, I would like to understand this. and I think I see how to do it. Let's sit and do it. So in other words, sometimes you come up with a topic for a research project where just as soon as you come up with the topic, it's pretty clear what you got to do to turn that idea into a paper. Let me give you an example. Just randomly off the top of my head, I wrote a paper about dark matter several years ago. Here was the puzzle. There are some weak astrophysical hints. We talked a little bit about this in the podcast with Priya Natarajan, that there are some weak astrophysical hints that non-interacting dark matter isn't quite up to the task, right? Ordinary cold dark matter models, the dark matter doesn't interact with itself at all. It just sort of moves under the force of gravity. It's weakly interacting, and that's so weak that it doesn't matter. So some people have said, well, what if it's strongly interacting? Then we can explain some of these astrophysical anomalies. And that may or may not be true. Honestly, I don't know. That's a hard astrophysics problem. But it's intriguing, right? From the particle physics point of view, because here's the problem with that. You can make the particles interact. You can just say, well, yeah, they bump into each other or they annihilate or whatever. But there's a relationship between the interaction strength and the abundance of the particles. When the particles interact strongly, they tend to annihilate away in the early universe. That's why weakly interacting particles are so interesting as dark matter candidates, because the weak interactions of particle physics give you roughly the right annihilation rate to give you the right abundance of dark matter to explain the observations. So if you just say, well, I want the dark matter to be strongly interacting, you have an extra puzzle about why there is the right amount of dark matter in the current universe. So I had an idea, which is, we have the Higgs mechanism in ordinary standard model particle physics where there's a phase transition. And before the phase transition, particles like the electron and the quarks were massless. And afterward, they're massive because the Higgs field changes its value and that changes the masses of these particles. So what if you did something like that, but did it with the interaction strength of the particles rather than their mass? Have a phase transition that changed the interaction strength of the particles. So they were weakly interacting in the early universe. They give you the right relic abundance. Phase transition happens, and now they're strongly interacting in some way, and that has astrophysically interesting results. So that was the idea. That's something you can come up with walking to work, feeding the cats, taking a shower, whatever. And the work that you need to do to turn that into a paper, in that case, is pretty straightforward. You just, start writing down models. Here's an action, a Lagrangian, let's figure out what the particles could be, how they interact with each other, calculate some interaction rates, the relic abundance, blah, 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 figure out how big the effects can be without running into other limits from all these other experiments we've done. Is a pretty straightforward set of things to do, and you set about doing it. Other projects, all you start with really is a vague hope. You say we've already said that the Hilbert space of the universe is about 10 to the 120 dimensional, right? That we said that earlier in the podcast. But the quantum field theory Hilbert space is infinite dimensional. So how do you reconcile that? Where do the extra dimensions of Hilbert space that you thought you had in quantum field theory, where do they go? That's a very open-ended question. I bring this up because some students and I spent a year thinking about it and didn't get anywhere. We did not publish anything about it. Other people have talked about similar things, but the structure of Hilbert space in a quantum gravity model or something like that is a vague enough question that you don't exactly know what to do. So you do exactly what you said. You talk to colleagues, you read papers, you sit and you think, and you scribble down some equations, whatever gets you in the right direction. Okay, I'm going to group together two questions. One is from Josh Powers. Suppose I look into the sky and see the light from Alpha Centauri showing that it existed 4 years in my past. Then I wait 5 years and see it again, indicating that it still exists. This implies that it, like me, has existed continuously for those 5 years, and it stands to reason that at any point in my subjective time, something was also happening at Alpha Centauri. Therefore, it seems like we do share a common present, even if we can't communicate to determine what events are simultaneous. This seems to contradict the idea that there is no universal present. What am I missing? And then David McBurney says, in the Biggest Ideas video on entanglement, you wrote the wave function for the universe with n particles, as psi of x1, x2, xn, n time. We often hear from relativity that statements like what is happening right now in Alpha Centauri are not sensible because time is relative and there's no such thing as now. If some of the end particles are on Earth and some are in Alpha Centauri and the location of the particles evolves per the Schrödinger equation, that seems like there is some preferred time. Is this another incompatibility of quantum mechanics and relativity? So in both cases, no, everything is fine. Don't worry. There's no universal present and there's no necessary incompatibility with quantum mechanics and relativity. I guess to get the second question first, once again, when you write the wave function of the universe for particles, right, x1, x2, x3, probably you're working in the non-relativistic approximation, for one thing, right? Because if you were relativistic, you probably should be doing quantum field theory. But that's just a little aside. The more important thing is what you've done in either case is chosen a frame, chosen a set of coordinates to extend across the universe. Relativity doesn't say you're not allowed to extend coordinates over the universe. It says that there are many ways of extending coordinates over the universe, and they're all equally good. So when I pick a reference frame, let's say I'm going to pick my reference frame, the one that is at rest with respect to what I am doing right now, as long as space-time is not very curved, if it's almost special relativity, I can extend a reference frame. So I can just go, in my mind, in a thought experiment, I can extend lines in a space-like direction at the moment I am right now and call that the same time as I am right now. Different observers moving at different rates would do that differently. So they would define now differently, but any one of them could write down a wave function psi of x1, x2, xn, and their time coordinate. And there would be a Schrödinger equation that told you how it evolved. And the Schrödinger equations would look a little bit different because they would be Lorentz transformations of each other. They'd be transformations from one time coordinate to another. But they're all equally good. They're all allowed. So it's not that there's some preferred times. There's many allowed times, and that's one of them. To Josh's question, it's sort of the same thing, but kind of from the opposite point of view. When you say, I see the light from Alpha Centauri showing that it existed 4 years in my past, that's already not quite right. It's 4 years in your past in a certain reference frame, namely the reference frame in which you and Alpha Centauri are more or less stationary, right? You and Alpha Centauri are essentially moving at the same speed. Compared to the speed of light, your relative velocity is very small. So there is a reference frame that has both you and that other star more or less at rest. It's in that reference frame that the light you're seeing from Alpha Centauri is 4 years in your past. If you were moving right past the same point in space, so still 4 light years away from Alpha Centauri, but you were moving, sorry, I shouldn't say that. You're moving the same point in space, but you're moving at 0.99999 the speed of light in the direction of Alpha Centauri, then the light you receive now from Alpha Centauri wasn't 4 years in the past. It was much less than 4 years in the past because you're going to get there, right? And from your point of view, it will take you much less than 4 years to get there. In the limit as you go at the speed of light, it takes you 0 years to get there from your point of view. So when you say that you make a series of observations and you see that Alpha Centauri is there now and it's there 5 years from now, and for all that matter, you could see it the whole time, you're still making an arbitrary choice of reference frame in which to do that. So that reference frame is perfectly usable. You're allowed to talk about what happens in that reference frame. You're just not allowed to treat it as somehow special or universal. Okay, Jimmy Summer has a priority question. I've listened to your colloquia on quantum spacetime, at least the one that's available on YouTube. I absolutely love the idea of your program. I was just curious, though, where are we with emergent spacetime in general? What are the most recent advancements and what still needs to be worked out? And if it all works out, will this essentially resolve the general relativity quantum mechanics reconciliation problem? For example, what do you think happens to black hole singularities in these emergent spacetime theories? I know we're still a ways from getting there, but do you have any personal conjectures? I think that the specific ideas that I've been working on with my friends and colleagues are very, very young and primitive compared to other more advanced research programs. So I think it's very promising. I think that, we start from a very simple set of assumptions about how quantum gravity works, the number of dimensions in Hilbert space, things like that. but we give ourselves very little to work with. We don't even give ourselves space, which everyone else does. So we have to build up a lot of things. And honestly, we haven't even built up light cones yet. It's kind of easy to see how they might arise, but we need to have a more dynamical understanding. We have kind of kinematics more than dynamics right now at the level that we're working at. And also all the really tangible quantitative results that we have are in the weak field limit, where gravity is not that strong. So we're not thinking about black holes or horizons or anything like that. So there's plenty to be done establishing that you can get Lorentz invariance. And for that matter, it's been fun to be thinking about gravity, but you also have to think about the rest of particle physics, the rest of the fields that we know and love, the gauge theories and the fermions and the Higgs boson and all that stuff. And I would like to get a better handle on how best to describe those things from a purely starting with nothing but a quantum wave function point of view, from a vector in Hilbert space. So there's lots to do. I don't even want to guess about what it's going to have to say about singularities or anything like that. Honestly, the thing about singularities, I think, is a low priority. I would rather understand black hole information and holography and things like that from this point of view, which I don't. So there you go. But I think that it can be done. We'll just have to see. James Nancarrow says, I read somewhere that if dark matter is a new subatomic particle, it might be its own antiparticle. And there are experiments looking for the annihilation of pairs of dark matter particles in the center of galaxies. How can a particle be its own antiparticle? What does it mean to be an antiparticle? Good. So you've put your finger on something that is a little sloppy in how particle physicists talk to each other as well as to the general public, which is they claim there's this thing called particles and this thing called antiparticles, which is a bit of a cheat. The reality is some kinds of particles have antiparticles and some don't. Like there's no antiphoton, for example. There's no anti-Higgs boson. There's just the particles. Some particles, if a particle carries a conserved charge other than mass, that's a separate thing. But if it carries spin spin does not count. Sorry, I shouldn't count spin, because you can always convert that into other kinds of angular momentum. If it carries baryon number or electric charge or something like that, then it will generally have an antiparticle that has the opposite amount of that conserved quantity. So charged particles are the most clear-cut case, where you have an electron, it has a negative charge. By the rules of quantum field theory and relativity, there has to be a positron carrying a positive charge. Dark matter particles are neutral. If they were charged, they'd be visible. They would be light matter particles, visible matter particles. So already there's at least the possibility that they do not have antiparticles. What matters, as it were, is not particles and antiparticles. This rule that, particles and antiparticles can annihilate, etc., is just a kind of sloppy rule of thumb. What matters are what interactions can happen, And the point is that there are interactions in the theory of many kinds of different dark matter particles where two dark matter particles can collide and convert into photons, for example. You don't need to use the phraseology of particle-antiparticle. You just say that the two dark matter particles come together and annihilate into photons. That's all you need. And from that perspective, it just makes perfect sense. There's mass and energy in them. There's no other conserved quantities. They can convert. That's a general quantum mechanical kind of thing. Okay, Matt from Sweden says, priority question. If, for the sake of clarity, we define global catastrophic risk as causing the unexpected loss of at least 100 million human lives within a 12-month period, what would, in your estimation, be the top 5 global catastrophic risks within the next 50 years? It's a perfectly good question. I can give you an answer. It's a priority question. I will do my best. I have no expertise in this. We do have an upcoming podcast where we'll talk about these questions a little bit in more detail. But I have not sat down and studied the relative rate of different global catastrophic risks. There's certainly a risk from, a huge asteroid hitting the Earth, but I think that the numbers there are very, very tiny. I would say the two most obvious choices are nuclear war, one way or the other. We still have a lot of operational nuclear weapons on this planet, and I know that we I don't know how old you are, but when I was a kid growing up, we were worried about nuclear war. I was in Ronald Reagan's America, and nuclear war was something that was on the agenda. But the weapons are still there. We've cut down the stockpiles, but the number of countries that have them only goes up with time. It almost never goes down. So that risk has not gone away. That's a real one that we should worry about more than we do, to be honest. And likewise, the other obvious one is bioterrorism. We're suffering through a pandemic right now, and I recently saw that it is plausible that if you don't just count the number of people who've died in hospitals and had their deaths attributed to COVID, but if instead you just count the number of excess deaths that we're going through now compared to what we had before the pandemic, you get a number over 20 million excess deaths because of the COVID pandemic. It's not that far. It's not an order of magnitude away from 100 million, right? And the thing about COVID is, it's especially nasty because you can get it and not know, and yet be able to transmit it, right? You can be infectious before you're symptomatic. And the good thing about COVID is it's not that deadly. Like you can get it and you can not die. It's easy to imagine a pandemic where you get the virus, you're not symptomatic, you can transmit it to others, and it kills you once you do get the symptoms. And that would be absolutely devastating, right? Much more devastating than COVID is. So that's another possibility if we don't get better at this whole vaccine thing, both inventing them and convincing people to take them. So if you want a top three, I will always throw out my favorite, which is solar flares. I don't really necessarily think it's in the top three, but I don't think we think about it enough because if there's a one chance per 1,000 per year of a gigantic solar flare that would completely wipe out all the electronics on Earth, we have no data on that because 1,000 years ago we had no electronics. So this is a plausible thing. It doesn't seem to be very likely to me, but it's completely conceivable that either solar flares or some other kind of occasional electronic huge event could cause huge devastation here on Earth. I don't know if 100 million people would die, but if you just imagine no electricity anywhere on Earth for, let's say, a few months, I can certainly imagine a lot of people dying. So anyway, that's something to not keep you up at night, I hope. We'll see. Going to group these next two together. Chris A says, I'm in conversation with a Christian who, unlike me, believes miracles are intrinsically possible and who demands less stringent supporting evidence than I would for such claims. She's inclined to believe that a very unusual event is miraculous, whereas I see it as surprising but not supernatural at all. I realize that one is supposed to update one's priors based on evidence, but in her case, poor evidence is more admissible than it would be with atheist priors. Can you suggest ways of discussing this productively in the context of Bayesian reasoning? And Paul Cousin says, imagine that you someday witness God performing miracles. As a physicist, you know better than anyone why you should not expect the laws of physics to be violated. Moreover, you know that the human brain is sometimes subject to very weird failures. Should Bayesian thinking lead you to put higher credence on a brain issue in this situation? If so, how can you trust your reasoning? So both questions have to do with how Bayesians should be thinking about the apparent appearance of miracles in the world. The first is someone thinks that miracles are happening all the time. How do we use Bayes against them? The second is, what if the miracle actually does happen? How do we make sure that Bayes doesn't mislead us? So one question is your priors. This is always the question with Bayesian reasoning. You come in to any particular experiment or situation with some prior credences, with some set of beliefs about how likely different things are. And I think, for the first question, for Chris's question, if you have someone who's already Christian and believes that miracles happen all the time, then you're in a difficult position. It's true, because, anything that happens, you go, oh, look, they're a miracle. It's very easy to see things like that. And I think that it's going to depend at a practical level on how honest your friend is about their reasoning abilities here, or the way that they reason into it. If you want to use your belief in miracles as just a license to believe whatever you want, no one's going to reason you out of that. You're just not being a very good Bayesian. But if you are committed to being a good Bayesian, but just someone who at the moment believes in miracles, what they should be asking themselves is, if there weren't any miracles, how often would we be seeing these things that we're seeing? Whether it's, I don't know, people coming back from being dead for a little while, or the Virgin Mary on a tortilla, or whatever it is, right? Whatever the claimed miracles is, someone gets healed. Would you expect these things to be seen just as frequently, or as frequently as you do actually see them, even if there were no actual miracles in the world? That's what you have to establish, because if that's true, if what you're seeing are things that you would expect to see in a miracle-free world, then seeing the miracles is not evidence that seeing the apparent miracles is not evidence or violation of the laws of physics. And if that's not true, if you actually think that the rate at which you would purportedly see these things is lower in your theory, purely physicalist theory, than it is in your experience, then that legitimately is evidence against the purely physicalist theory, and then you have to cope with that. Of course, in practice, it's very, very hard to do these calculations. That's why, Bayesian reasoning is a good aspiration sometimes, but you have to, when in putting it in practice, we cut corners. There's nothing else that we can do. What is the frequency at which you should expect to see the Virgin Mary on a tortilla, or someone who has cancer suddenly go into remission? I don't know. In the absence of God's intervention, it's bound to happen sometimes, but it's very hard to calculate an actual number. But that's what you would try to tell your friend. Of course, then the other question is their priors. Do they think that it is more likely in the absence of any data that miracles are happening all the time, or more likely that the laws of physics are being obeyed? Some of us would say, look, a world that just obeys the laws of physics all the time is just simpler, is just easier to comprehend than a world in which the laws of physics are usually obeyed, but then occasionally miraculously violated, and therefore you should put a higher prior on the physicalist world than the miracle world. But that's, if they don't want to accept that, everyone is entitled to their own priors. Likewise, okay, for Paul's question, if you are a good physicalist as well as a good Bayesian, what kind of miracles would it take you? Would it take to convince you otherwise? Because I am a big believer that a good Bayesian should not rule out supernatural possibilities a priori. I never bought into this very common claim of methodological naturalism as part of science, that science has to assume naturalism from the start. I think that science concludes naturalism because it's the best fit to the data. It doesn't assume it from the start. It's methodologically empiricist. It judges whether how to develop these theories on the basis of data, on the basis of observations of the world, rather than on the basis of pure thought. And therefore, if there are things that are better explained by miracles than by the laws of physics, then that should move your credences toward the belief in miracles. Now, as Paul says, it could also be a brain issue or something like that. And I think you should just be honest. I don't have numbers to give you, but you shouldn't, it is possible that it is a brain issue. People do hallucinate, right? Or people misremember or whatever. Those are all absolutely possible. In my current state of belief about the world, if I saw something that looked purportedly miraculous, I would put a very high credence on it being a mistake on my part, either a brain issue or a hallucination or an optical illusion or whatever. But if it kept happening, and if it was, reproducible or there's good evidence for it, then that would move my credences in the other direction. There's no hard and fast cutoff. That's the great thing about Bayesian reasoning. You just accumulate evidence and keep going. You keep going where the evidence is pointing you. Peter Solfest says, what do you feel is the most effective way for someone in your position to interact with our democracy in order to promote the policies you are in favor of, e.g. voting, political conversations on your podcast, talking directly with representatives, donating to interest groups, etc.? I think that it's going to be different for different people. I think voting is true for everybody who can vote, right? I'm a big believer in voting. It's not an obvious thing, as we discussed with Herb Gintis on the podcast. The rational case for voting is a little tricky, but I think it's makeable depending on what your goals are. But then, beyond that, you need to do a little bit more. You can do a little bit more. I don't mind people who don't do a little bit more. I would like it if people voted. I don't think talking directly with representatives is usually helpful compared to other things because we're in such a polarized situation these days where the real question is, who are the representatives? Are they in one party or the other party? Like once you have that, mostly the representatives will be doing pretty predictable things. Now, there are obvious counterexamples. Fans of American politics will know that in the U.S. Senate right now, which is nominally 50-50, but it's really, we have a Democratic president and vice president, so Democrats get to win on the tiebreakers. So Democrats should have a majority in the Senate, but we have two senators who like to be ornery and contrarian and not go along with the rest of the Democratic agenda. So effectively, you don't have a majority in the Senate, and it's very hard to get things done. So if I lived in states where those senators were representing me, then I might try my best to interact with them directly. Otherwise, doing things that can make people think or move people in the direction you think are moving them, whether it's having conversations on the podcast or donating to interest groups. As you know, as many people know, I don't know, depending on how long you've been listening, but I am happy on the podcast to talk about the ideas associated with politics. I am not happy to talk about political campaigns or things like that. I'm not stumping for individual candidates and so forth. I think that even having politicians on the show, which I would do under the right circumstances, but it's not my first choice because they have a different agenda. They have an agenda of, in the cynical view, getting elected. But even in the most idealistic view, they have the agenda of getting their agenda passed, right, in Congress or whatever, which is different than my agenda, which is understanding how the world works. So if I'm talking about politics on the podcast, it'll be talking about political ideas with professors more often than it is talking with actual politicians. And also, if I'm influencing people by talking on the podcast, what I hope to be influencing them to do is to think for themselves in ways that I think are good ways to think. The conclusions people reach, we'll see. People should reach their own conclusions, but they should do it in ways that are rational and hopefully exhibit some compassion and empathy for other people in society. That's what I would like to influence people to do. Ingrid Gorman says, priority question. I don't understand how to reconcile a theory of all time existing at once, like a loaf of bread, and how we can also understand emergence, evolution, for example, and other things that took time to evolve. So one sub-footnote here in this question, because I think this comes up elsewhere in other questions we'll get to. The word emergence, which I love using, I use it all the time, it's not the perfect word for what I'm describing when I talk about emergence, because the emergence I'm talking about is not a process happening over time. It's the simultaneous existence of different descriptions of some system and what it's doing. Like we already said, you could talk about the gas in a box as a set of atoms or as a fluid, right? That's emergence, even though it's not like the set of atoms are turning into a fluid or anything like that. Okay, that was a footnote. To actually answer your question, the trick here is that presumably what you're talking about is the doctrine of eternalism, the block universe view of reality, which I happen to subscribe to. But the way that you phrase it is a theory of all time existing at once. And the worrisome part there is the phrase at once. So I would never say that because that phrase at once indicates a particular time, right? That's what at once means, once, one time. But it kind of doesn't make sense to imagine that all time exists at one time, because all time is a bunch of different times. The thing that an eternalist would say is all time exists. All moments are equally real. The current moment you're in is real, but future moments are also real. Past moments are also real. They're not all real at the same time or at once. That would make no sense, but they're all real. And if it ever seems weird to be thinking about that, just switch in your brain the question from time to space, right? Because in relativity, we're taught that time and space are very, very similar to each other. They're not exactly the same, but very similar. And so no one has a problem thinking that all points in space exist, right? You're located at only one. I mean, if you coarse grain so that you count as one point in space and other places count as other points, okay, you're located somewhere in space. That doesn't lead you to doubt the existence of other points of space far away. They just all exist, but you happen to be located at one of them and you count your position relative to others. That's how time works for an eternalist. Just like all the points in space are real, all the moments in time are real, you at one moment happen to exist in that moment and count your location in time relative to other moments. It all works in more or less the same way. That's, I think, the best I can say. Benjamin Barbrell says, poetic naturalism recognizes the ability to tell different kinds of true stories about the world. These stories use different concepts, applying different domains of validity, but need to be consistent with each other. The only way I can imagine to ensure this consistency would be a tree-like hierarchical structure, where the domain of validity of stories closer to the trunk would encompass those of emerging levels higher in the branches. The existence of this structure is what I always assumed reductionism was. Each level can in principle reduce to a lower, wider level. Reading the big picture, I understand that what I describe is not quite what you have in mind. You don't appeal to reductionism. And it seems to me the various discourses on the world need not be organized in this fashion in poetic naturalism. Yes, I think that you got it. That's exactly right. And part of it is because I'm just trying to be careful not to confuse what actually happens with what must necessarily happen. So in this picture of different ways of talking about the world, what I say is there are domains of validity, domains of applicability. I was told not to say validity because philosophers use validity to refer to the validity of a logical deductive argument. Okay, so domains of applicability, although validity sounds better to me. So in the space of all possible things that can happen in the world, different theories might accurately describe what's going on in some circumstances, but not in others. For example, once again, if you go to the gas in a box, since there are usually so many atoms and molecules of gas in the box, the fluid description also works to describe what happens in that box. But if you only had one molecule in the box, then there's no fluid description that would work. But the atomic description still works perfectly well, right? So the atomic description is a little bit more comprehensive. It has a domain of applicability that is a little bit broader than the fluid description does. So if you imagine plotting, some Venn diagram, you would have the domain of applicability of the atomic description, and then a subset of that would be the domain of applicability of the fluid description. It happens to be the case that in many, many known and understood and familiar examples of emergence, all of the theories are entirely subsets of other theories. So in other words, there is a hierarchy. There's like some big comprehensive theory, and there's some emergent theory that is a subset of that, and a subsequent emergent theory that is a subset of that, and so forth. And the usual story is something like physics, chemistry, biology, psychology, sociology, or whatever, right? Those are all individual theories that work under different circumstances that are supposed to be consistent with each other, but something like sociology has a much smaller domain of applicability than particle physics does. Domain of applicability doesn't mean it's the best way to look at it. It makes no sense to describe human beings using particle physics, but you don't want your human beings to be incompatible with particle physics either. You want them to obey those rules, okay? Having said all that, and I think that's what Benjamin's guess or original thought was. But having said all that, this fact that higher level theories, or what we call higher level theories, fit inside the domains of applicability of lower level theories is in no sense necessary. In the space of how we could possibly imagine knowledge being organized, it's very easy to imagine two completely non-intersecting domains of applicability, or two domains of applicability of different theories that intersect without one being a subset of the other, right? Some overlap, but incomplete overlap. And I think that those kinds of possibilities might even be relevant for questions of things like strong emergence and downward causation and things like that. So You're exactly right, Benjamin, that I do not use reductionism in this picture. Reductionism is a specific kind of emergence where you say not only is my higher level theory a subset of the lower level theory, but the lower level theory is made of small pieces, collections of which are the ontological elements of the higher level theory. In a very straightforward way, that does make sense in a lot of circumstances, like with the atoms in the gas, okay? The little cubic millimeter of gas in a fluid is a whole bunch of molecules, okay? It's literally a collection of those little smaller pieces. But there's other cases where that doesn't work, and partly why I'm so sensitive to this is there's something called quantum mechanics. And in quantum mechanics, you can say the classical world emerges from it, but not because one big classical thing is made of little tiny wave functions. There's still only one wave function for the whole world, right? The way that the classical world emerges from the quantum world is much more subtle than a naive reductionistic picture. So I'm trying to separate out all the different ways things could possibly happen from the specific ways they happen in the real world. That was the point of that discussion in the book. Stuart Haynes says, how do you find living with an electric vehicle? Has the range ever been an issue? What do you like most about it, and what do you miss the most from your prior vehicle? So as some of you know, I have a BMW i3. If you've seen one of these on the streets, you'll recognize it. It's a tiny little car. It's about the size of a Mini. It's kind of space age looking. We call it the space buggy. And one of the fun things about it is that it's available, or was available. I think they're canceling it. It has been available with different interior packages made of different materials. So the interior of our space buggy is like a mixture of fabric and leather and carbon fiber and wood. Oh yeah, wood. The wood is the steering wheel. So it's like a kind of postmodern pastiche of different kinds of things. And it's electric, and it's not at all popular, this particular car. And the reason why is they didn't even try to give it a long range. The range is like 100 miles purely electric, maybe 120. And then there is a range extender, which is like a little tiny putt-putt engine that is gas-driven. But it took me a while to figure this out. The gas-driven putt-putt engine never drives the car. All it is, it's literally, I call it a putt-putt engine. It's literally from a moped originally, I believe. And if you're running low on the electrical charge, you can run the range extender and it will recharge your battery. And then you're still running on electric. So the actual powertrain of the car is purely electric, but there's sort of like a backup source of electricity, and which I've never used. We've never used the range extender. Many people, for very good reasons, get very uncomfortable if their range is less than 300 miles, right? And something that I think is not said out loud enough, the reason why that's a problem is because it takes time to charge your car. You know, the range on internal combustion engine car isn't much more than 300 miles, but you can go to the gas station and a minute later you're full up and then you can keep going, whereas it takes time to charge your car. So that's why things like fuel cell cars are interesting ideas, but they haven't really become practical yet. Anyway, so the whole point of the i3 is you wouldn't want it as your only car. And you wouldn't want it as a car at all if you led the kind of lifestyle where you're driving 100 miles every day or more. But if you live in a big city or even in a reasonable sized suburb, and it's your second car, if you're a two-car household, as we are, then it's perfect. I love it. I love that car to death. I mean, we have a gas car now for road trips, etc., and we have the space buggy, the i3, and almost all the time we're driving the i3 when there's a choice because it's quiet. You get this pleasurable experience of driving by the gas station and never stopping. It's very, very zippy, even though it's tiny, right? The acceleration, it doesn't go very fast. Its top end speed is not competitive with a Tesla or anything like that, but its handling and initial burst of speed are very, very good. So you really feel like you're totally in control of what the car is doing on the road. And the aesthetics are cool, and it's just kind of like a very fun car to drive. You just are smiling when you're driving the i3. So we've been very, very happy with that, but I totally get that it wouldn't work if if it was your only car, if you had a big family, or for many other things. It's a very niche kind of vehicle. Gillis15 says, I read yesterday the NFL team who won the coin toss since the introduction of the current NFL overtime rules has only lost once. Should the NFL change its overtime rules to match those of college football, where each team gets at least one possession from the 25-yard line? I have no idea whether it should or not, but I strongly suspect it should. So I'm not a football fan anymore. I used to be a football fan as a kid for various reasons. I've stopped following football, so I've not followed these recent controversies about the overtime rules. The only reason I'm answering this question, I have nothing interesting to say about it, but I have this feeling that sports leagues are way too conservative about changing obviously bad rules. And so even though I don't know the details of this situation, my strong suspicion is that they should change the rule. There have been so many complaints. And it's one of those things where apparently this year the rule has been coming into being very relevant in the playoff games over and over again. But you should have known years ago that this was a silly rule. Like it's some kind of sudden death overtime where the first team to score wins, which might make sense in soccer, regular football, but not in American football. That makes no sense at all. So yeah, they should change it. That's my thought. Johan Löfgren says, one of Weinberg's 3 conditions for when a physical system can be described as an effective field theory is something called cluster decomposition, which is typically called a type of locality constraint. But we also know that quantum gravity will need to have some non-local aspects. Does that mean that treating the core theory as an effective field theory is actually mistaken? Or can the core theory manage to preserve cluster decomposition while still being non-local? This is a good, technical, but very good question. The point is that the core theory is not supposed to account for gravity in those regimes where the non-local aspects would be relevant. So it's true, you're correct, that there are reasons to believe that quantum gravity has some non-local aspects. But what are those reasons? Those reasons have to do with black hole information loss or something like that, or, very, very unlikely phase transition, bubble nucleation kind of things. Nothing that is in the everyday life regime. The whole point of the core theory is that it correctly describes everything that we know about, including gravity, in the everyday life regime, in the solar system, okay, on the Earth, the sun. And there's no non-locality that you're expecting from quantum gravity. So the core theory is resolutely an effective field theory and does obey cluster decomposition. And it has a domain of applicability, as we were just talking about. And that domain of applicability does not include black holes or the Big Bang or any other places where non-locality is expected to become important. Mark Gregor Pierce, I don't know how to pronounce his name, sorry Mark, says, I've heard many physicists express disappointment when experiments designed to find problems with Einstein's general theory of relativity fail. They say that finding problems with general relativity would open doors to new physics. From my perspective, experiments that once again support general relativity simply show Einstein's enduring brilliance. I wonder where you stand on this topic. Well, look, many things. So I guess the big picture answer is all physicists are always going to be disappointed when a theory that somebody else came up with passes an experimental test, roughly speaking. Because if you're doing the test and there's 2 possibilities, you're confirming an existing theory or finding an anomaly, finding an experimental difference between what the real world is doing and what the theory is doing, it's much more interesting to find an anomaly, right? Because that means that there's a better theory out there that maybe you don't have yet, but you can start looking for it. Whereas if you're just reconfirming an existing theory, that's very, very good work. It could be very, very valuable, but it's not going to lead to a breakthrough in inventing a better theory. So that's why people are disappointed by that. If you're Professor Einstein, you can take personal pleasure in having your theory pass all these tests. That's great. So that's roughly, I think, the perspective that working physicists have. They want useful new input into their task, into their program of building new theories. But also, I wanted to comment because you said the experiments that support general relativity show Einstein's enduring brilliance. And I don't think that's right. I think there's a little bit of a misunderstanding there. If Einstein would not be any less brilliant if an experiment showed a deviation from general relativity. Einstein invented general relativity. That was his brilliance. That's already shown. It's a wonderful theory for all sorts of reasons, and the fact that it works in the easy cases is more than enough to establish Einstein's enduring brilliance. What these experiments are establishing is not the brilliance of some human being, but the particular way that nature works, that some theories have certain domains of applicability that are quite broad. The amazing thing about general relativity, I mean, it's amazing from one perspective and perfectly natural from another perspective, is that you invent it by thinking about the solar system. Like Einstein in 1915, he didn't know about cosmology or black holes, right? So he knows about Newtonian gravity, he knows about relativity, special relativity. And on the basis of that, he says, okay, what's the simplest way to reconcile these? And he invents this brilliant idea of curved space-time. And he says, okay, what's the equation that curved space-time should obey? Buy my book. For y, the right equation pops out in the way it does. But the point is, the equation he comes up with is more or less unique. Given you want a relatively simple equation that relates the curvature of space-time to matter and energy, you're going to come up with Einstein's equation. Einstein did it first, but you're going to do it. There weren't many choices. And the amazing thing is, it also works for pulsars and black holes and the expansion of the universe and the microwave background and a million other things, right? We understand why on the basis of how field theory works. General relativity is a field theory. It's a classical field theory, but still, in the general realm of field theories, you would expect field theories to work on long length scales and to break down at some shorter length scale. So if general relativity works in the solar system, you'd expect it to keep working cosmologically. Not necessarily not with 100% certainty, but that's the way to bet. So I'm all in favor of people looking for deviations from general relativity in cosmology, but I don't expect them to find any. Ken Wolfe says, in the Mindscape podcast episode, Quantifying the Shape of Stories, Peter Dawes talked about some of the potential dark sides of storytelling. Is there any particular popular story, be it a novel, movie, or television series, that you think has an underlying message or moral which you regard as being fundamentally wrong or misguided, and why? So, I debated about this question because I don't have a good actual answer. I mean, I could, say that, I don't know, some of the Ayn Rand's novels have a bad moral message about selfishness, or, Leni Riefenstahl's movies that were propaganda for Hitler, those are bad, or the pro-slavery movies from D.W. Griffith, bad. Okay, but those are not, currently popular TV properties or something like that. And I'm sure the answer is yes. I'm sure that there are shows on TV right now whose message or moral I disagree with, but I can't think of any honestly off the top of my head right now. So I was originally thinking that it's not worth answering since I have no good answers to give you, but there's a underlying issue here that is at least worth, not answering because I don't know the answer to it, but worth bringing up, which is, what does it mean to say that a story has a message or moral, right? We all know it does. I'm not arguing that stories don't have messages or morals, but in some sense, think about this potential point of view. A story is just a recounting of things that happen, and they don't happen in the real world. It's a fictional story, but it's a set of things that happen in this imaginary world, right? Okay, but we know you can't derive aught from is. So what does it mean to say that this particular recounting of events has a moral or a message? And presumably what it means is that there is some kind of justice that occurs, that, people who make the right choices are rewarded, people who make the bad choices are punished. And most of the time, I think that that's actually true, but sometimes it's not. Sometimes we know of stories where the clearly heroic character doesn't win in the end, right? The character does all the right things and nevertheless comes out worse for wear. And so I can't quite condense what that means into a simple statement. How do we know what the moral is if they fail? And I think that there's some complicated kind of subtle subtextual thing about the way characters are portrayed as either heroic or despicable or whatever. But I'm not exactly sure, how you could objectively classify those things. So I think that the morality or message of a story has to do with which actions are treated as heroic or admirable. But I couldn't tell you what the rules are for saying, oh, yes, this story is treating these actions as heroic or admirable. I'm just not sure. So I don't know what the answers are, but I thought that was an interesting thing to think about. So I'm glad that you asked the question. Jonathan Sirocco says, I wanted to know your thoughts about one common criticism of string theory, namely the falsifiability of the theory. And then there's more to the question you can read in the comments on Patreon. But that's basically the question. You know, what is the issue with falsifiability and string theory? So there's a couple issues. I mean, one is the whole idea of falsifiability is a little bit overblown. As I've written about in blog posts and papers, Popper, when he was talking about falsifiability, was gesturing toward two very important features of a good physical theory. One is that it should be definite. There are some things that the theory says are potentially allowed to happen, and some things that are not, okay? It cannot literally account for everything, right? And the other aspect that he was gesturing toward is that there should be some empirical way of judging the success of the theory. That's what really matters. It's really those two things that really matter. And he, attempted to sort of sum them up in this single criterion of falsifiability, but it didn't really work. Philosophers of science these days don't buy falsifiability as the right way of demarcating science from non-science. Physicists love falsifiability because it's a one phrase, right? You don't have to think that hard. Like, they talk to real philosophers of science and it sounds like you keep talking and it's hard and it hurts your brain. You don't want to bother. Whereas falsifiability is just a little motto you can put on a bumper sticker. That doesn't make it any more accurate. So there's issues with using falsifiability in a too simplistic a way. That's one thing. But the other is, think about, let me, before directly addressing string theory, let me give you an example of a failure mode of thinking of falsifiability as the most important thing in the world. One way that a theory might not be falsifiable is if there are free parameters in the theory, right? Like Newtonian gravity has a free parameter, Newton's constant of gravitation. And you measure it, because the theory is accurate in a certain regime, you go just measure the parameter. But if you don't know your theory is right in a certain regime, you might have a parameter with the feature that as that parameter gets smaller and smaller, it becomes harder and harder to see any effect of the theory whatsoever, right? Like strings are very tiny, so it's hard to see them. Dark matter interacts very weakly. In the limit, as dark matter doesn't interact at all, you will never see it in an experiment in a lab here on Earth, okay? So does that mean that the theory is not falsifiable? Because there are values of the parameters that would make the direct implications of the theory unmeasurable. And I say this because many people talk as if it would. That counts as not being falsifiable if there are free parameters that would basically hide the theory from your view. So here's the problem with that. What if you find the theory's right? So an example is cosmic strings, okay? Cosmic strings are different than string theory. Cosmic strings are big cosmic things left over from the early universe, not little tiny things that are supposed to be elementary particles. But there's this idea that there are leftover cosmic strings from the early universe that, could have a role in current astrophysical dynamics. But there's a free parameter, what we call the tension of the string, basically the energy density along the string. And if there are lots of strings and there are very dense, high tension, it would be easy to see them. And in the limit, as the tension of the string gets smaller and smaller and smaller, then you would never see them, right? If the tension is arbitrarily small, there'd be zero observable effects. So this perspective would say, okay, that's not a falsifiable theory. We should not count it. The problem is, what if you measure it? What if you do detect it? What if you measure a specific value of the theory, of the tension of the strings, because you've seen some gravitational lensing event or something like that? Now you've tied yourself in a philosophical knot where you have to say, well, I can't believe the result of that observation because I've decided this is not a scientific theory. And that's just silly, right? Because falsifiability is not the right way to demarcate scientific theories from non-scientific theories. So that's analogous to the string theory situation, because string theory, like other approaches to quantum gravity, like loop quantum gravity, etc., has, hand-wavy ways that maybe it could someday lead to experimentally testable results. Large extra dimensions, supersymmetry, things like that. It's a tenuous set of connections between the predictions of string theory and potentially observable things, but they are there. And we could easily imagine a situation where over the next few years or whatever, we suddenly make a series of experimental discoveries that convinces us that string theory is on the right track. But it's also very plausible, in fact, way more likely, that even if string theory is true, it continues to hide from our direct experimental probes, roughly because gravity is weak and quantum gravity is hard to experimentally test. Nothing specific with string theory, just gravity is the problematic thing here. So people have pointed out that in string theory, there are extra dimensions. There are many ways to hide those extra dimensions, and every way leads to a different low-energy version of physics. By low-energy version of physics, I mean, for us, the core theory, the standard model of particle physics with its specific forces and matter particles, etc. And there are different ways that could have turned out if we lived in a world with a different compactification of the extra dimensions. There are so many possible ways to compactify the extra dimensions that you can get almost any specific version of low energy particle physics. So people make the criticism that therefore string theory predicts every possible thing, therefore it predicts nothing, therefore it's not a theory at all. And I don't believe that either. I mean, I think that's just sloppy reasoning on the basis of people who don't like string theory because, as I said, that's the low energy physics of string theory. String theory comes into its own at high energies, near the Planck scale, where it makes definite predictions for what would happen if you scattered two strings off of each other. Now, even there are subtleties because of dualities and so forth, but it's very much in the realm of things where there are thought experiments we could do that clearly show that things are behaving in a stringy fashion or not behaving in a stringy fashion. There's no guarantee we'll ever be able to do that, but in sort of the underlying story of what Popper had in mind when he invented falsifiability, the fact that string theory says that certain things would happen and certain things would not is what matters, not whether or not you and I can ever actually do those experiments. Okay. Felix Dare asks a priority question, and it's a long one. Buckle up. So say if we take the cat out of the thought experiment, Schrodinger's cat, and focus instead on what is going on with the atom. We have a machine which randomly selects a single atom from a sealed box containing many identical radioactive atoms. The machine takes a reading at the exact point of the atom's half-life. If it is decayed, then a macroscopic event A is triggered, like a bell is rung. If it is not decayed, then macroscopic event B is triggered. A firework rocket goes off, let's say. I would argue, says Felix, that the atom which is selected from the container is special in some very particular way. It alone among all the atoms in the room is able to impact the wider world around it. Each of the macroscopic events in question could have occurred spontaneously without any intervention from the machine, but the chances of that so happening are extraordinarily unlikely. If I can apply a version of what I understand to be your explanation of the multiverse theory, the rules have been rigged so that the universe can split into only one of two outcomes, each of which was always possible, but neither of which would have otherwise been expected to occur. The laws of physics ascribed to the atom are exactly the same as for those left behind in the container, but the selected atom is special in a very remarkable way. It has been given, in effect, agency to choose which event will occur. This agency comes not from anything particular about that atom, but rather from the structure of all the other atoms around it, the machine, the bell, the firework, etc. If we are prepared to make this leap, then the same agency could equally be ascribed to the structure of the atoms inside the human brain, albeit on a much more complicated level. I may perhaps be restating the problem of consciousness, but it seems to me that the above perspective provides a route by which the purely quantum properties of a particular atom or other subatomic particles can reach out to influence and perhaps even be said to communicate with the wider macroscopic world. Okay. So I forget whether I edited your question. Sorry about that, but there's not a question mark that is lying at the end of that. I will try to comment on what you're getting at, because there are a couple of comments here. One is, I think the basic picture is perfectly plausible. The basic picture that individual quantum events at the atomic or subatomic level will usually be unnoticeable to us, right? The decay of a single atom is not something, it happens all the time in our bodies and we don't notice. But in exactly the right circumstances, you can amplify those quantum events. This is a well-known thing. You can take a quantum event, and if it interacts with the surrounding materials in exactly the right way, that amplification can become macroscopic. No problems with that whatsoever. Completely on the right track there. Now the question is, there's two questions. One is does it make any sense to assign the word agency to this? And I don't think there is. That's not what I mean by agency anyway. Agency in my mind specifically makes sense as a description of a situation where there is some immensely complex situation where you can't actually model all of the moving pieces that are doing their thing, and therefore it becomes useful as an emergent higher level description to ascribe an agent making choices, or to use that language, that ontology, to describe what is going on. A single atom, just obeying the Schrödinger equation, is not in that situation of enormous complexity where I have no better way of describing it than as an agent making choices. So I would not want to use that word. But what you're getting at with the human brain is, in some sense, I think, perfectly reasonable. The thing that happens in the human brain is, I think, the collective behavior of a whole bunch of things governed by the laws of physics. And so it's absolutely the case that whatever is happening in the human brain is a bunch of atoms doing their thing. Now, there's a specific question about whether or not the quantumness of the individual atoms matters. You know, when you hit a baseball and you follow its trajectory, that baseball is made of atoms, and atoms obey the rules of quantum mechanics, but who cares? The baseball is going to obey the classical equations of motion. So the question is, in the particular configuration of the human brain, where we think that the human brain is much more complex than a baseball. There are a lot of moving parts, and the moving parts matter in interesting ways. Individual neurons talk to each other, signals get fired back and forth in a pattern that is hard to predict exactly what's going on. And those things that happen are generally thought of as neurochemical, right? They're generally conceived at the level of neurons doing things under certain circumstances, and you can talk about the action potential and, you know, what signals the neurons are receiving and what ones they're giving out and so forth. But you could go down to the level of individual atoms. I mean, neurons are small, but they're much bigger than atoms, okay? There's a lot of atoms in a neuron. So usually the description we use is at the neuron level. The question is, I'm finally getting to it, is it easy or at least plausible to imagine circumstances under which a 50-50 quantum measurement possibility in an individual atom can lead to different behaviors in a neuron that would lead to different behaviors in a macroscopic person? And that I honestly don't know the answer. It is completely plausible to me that that could happen. I suspect it is rare. I suspect that because the brain has a lot of particles in it, many, many, many particles, you know, even though it has a lot of neurons, again, those neurons have a lot of atoms in them. And these signals, these electrochemical signals, are still involving a lot of atoms. I suspect individual quantum choices or measurement outcomes usually wash out. But if you're right there on the precipice, halfway between one possibility and another, maybe a single quantum measurement event really does matter. I don't think that has anything to do with it's not a necessary part of talking about consciousness. Let's put it that way. I believe that you could do everything that is necessary to explain consciousness using classical physics or using just the higher level neuron description. But I don't know about that. I'm being open-minded about that. Maybe someday we really do need to take into account these quantum events to really think about what is happening in the brain and it becoming amplified up to human actions. That's an open possibility. Noble Gas says, as Bayesians, we can never assign 0% probability to anything. Some scenarios have vanishingly small chance of being true, but in an expected value calculation, the badness of them is so great that it overwhelms even the smallest probability. These things cause me a great amount of psychological distress, even though I assign a very low likelihood to them. For example, I lose sleep over simulation arguments with dystopian outcomes and quantum immortality. I know you've written about these topics, but you don't seem distressed by them. What advice can you give to people who know these things are unlikely but still worry about them? Well, I think there's at least two things going on. You're right in the basic setup. If you believe in both quantum mechanics and Bayesian reasoning, then there are very unlikely but very bad events. So the two things that I would emphasize are, number one, they're typically very unlikely. So even if they're very bad, there's no guarantee that even if the badness is large, the product of the badness times the likelihood is large. You would have to do a very, very careful analysis of that. You know, back when the Large Hadron Collider was firing up and people asked scientists, is there a chance it destroys the Earth? You know, the honest scientists had to say, well, there's a chance. There's always a chance. They eventually gave up saying that. You know, John Ellis, when he was interviewed on the Tonight Show? No, Jon Stewart's show. You know what the show is. He just was asked about whether the LHC could destroy the world, and he said no. That was it. That was his answer. No, it won't, because he knew that careful parsing of tiny probabilities was not useful in that particular atmosphere. But the point is that the scientists did very, very carefully think about the probabilities, wrote papers about them, did calculations, and the probability is never zero, but it's so very, very, very tiny that they judged it not worth thinking about. I think that's generally the case with these kinds of situations. The other one, which was pointed out by Martin Rees on the podcast episode that I did with him way back when, was if you're going to focus on these very, very unlikely bad events, you have to admit the possibility of very, very likely good events, right? Like the LHC will give us free energy, violating the conservation of energy and providing free power for all of human eternity. There you go. It's possible. Maybe the LHC will allow us to cure all diseases, right? So you talk about simulation arguments with dystopian outcomes. Yes, but there's also simulation arguments with utopian or heavenly outcomes, right? And I think you should just ignore all of them. I think if they're truly very, very low probability, the real thing is not a conviction that the probability is so low that when you multiply it by the badness, it's still small, but a humble recognition that the probability is so low that you don't know what the probability is, right? That's the threshold in my mind that makes it not worth worrying about. Once we're talking about things that are so unlikely that it is just moonshine for me to pretend that I know what the probability is, I'm not going to worry about those things. There's enough real world things out there to worry about and to be happy about. Gregory Kusnik says, the hard problem of consciousness is usually framed in terms of explaining how subjective experience can emerge from the purely physical interaction of particles. But no one seems to wonder how, say, natural selection emerges from fundamental physics. Indeed, 50 years before the formulation of quantum physics and a century before Watson and Crick, natural selection was understood as a logical consequence of imperfectly replicating information. Its explanation is completely disconnected from the underlying physics of the molecules that carry that information. Do you think consciousness could be like that, and its explanation will be found not by mapping the brain down to the level of particles, but by developments in cybernetics and information theory that shed light on the nature of complex systems without reference to the underlying physics? Yeah, I think that's more or less completely obviously true. I would be absolutely shocked if anything about fundamental physics was useful in explaining consciousness. The only point that I have to offer in debates about consciousness is that we have very, very little reason to imagine altering fundamental physics to help explain consciousness. So in fact, this is exactly my point of view, that we should think of it as an emergent higher level phenomenon. And I would be very surprised if you couldn't even think about, you mentioned information theory and cybernetics. Those will undoubtedly be useful. I think that understanding the brain is going to be the most useful thing, right? And I know that people don't agree with this. The argument against this is that you can understand everything that the brain does and still don't have a handle on subjective experience. But if we I believe that if we truly understood everything the brain does, that when you feel sad, something is going on in your brain. When you experience the color of red, something else is going on in your brain, we would eventually be done. We would just say, that's it. This is what is happening. And then the phrase, I'm experiencing the color of red, is a way of expressing something going on at the level of neurons, which is also something going on at the level of atoms and particles, right? But we don't need to know what that is to have an explanation, just as with natural selection. Jay says, I appreciate it if you could discuss the physical interpretation of fields. I more or less understand the mathematical definition, but for example, I don't understand where the fields come from physically. Were they created at the Big Bang or already present? Are they expanding in lockstep with the universe, or is the universe expanding via fields that already exist? So I'm worried, Jay, that you have a kind of an intuition about fields that is not quite accurate. Fields are properties of the universe that are located at every point in space-time. So they are coexistent with space-time itself. They're not created or destroyed, the fields themselves. The field could have a value of 0 at some point. So the particles that are excitations of the fields can be created or destroyed, but the fields are just there. They come along with the ride once you have space-time. You can have different theories where different fields come along with the ride, but in any given theory with certain sets of fields, there they are. So what that means is that at every point in space, there's a set of field values for the different fields, for the electron field, for the electromagnetic field, and so forth. As space gets bigger, number one, you have to ask what you mean by that, space getting bigger. You know, in cosmology, we have a perfectly good understanding of what we mean by that. We mean the distance in between galaxies is increasing. But at the fundamental physics level, we're less sure that we know what we mean by that. In classical general relativity, there are an infinite number of points between any two locations in space. And so when we say space expands, there are still an infinite number of points. I mean, there's no mathematically rigorous sense in which there are more of them, even if they doubled in number, if you know what I mean. But anyway, the usual conventional picture is space gets bigger, and at every point in space, the fields are there. They're not causing the universe to expand or anything like that, but they have energy, and that energy does affect the expansion of the universe. Jim Watson says, in the expanding universe, do we think the Planck constant is really constant, or is it that the Planck constant is changing with the expansion of space-time? Well, we certainly think it's constant. You can try to do measurements, asking yourself how it would change, how observable things would change if Planck's constant were different. But that's exactly like the speed of light in the sense that there's a very real sense in which the Planck constant is just equal to 1. You can always choose units in which that's true. It's not so much a constant of nature as it is a conversion factor between different things going on. In particular, it's the conversion factor that relates quantum effects to classical ones. And so if you think about what it would mean to change the speed of light. The speed of light is an easier example, so let me talk about that. We can relate it then to Planck's constant. If you talk about changing the speed of light, you think that makes sense. There's a certain number of meters per second, right? 300,000 kilometers per second. How hard would it be to change that number? But what you're really doing is changing the definition of the meter or the second. You can always define the speed of light to be 1 light second per second. And in particle physics, what it works out to be is that the definition of, I forget which way it goes. I think that it's a definition of a meter is given in terms of a certain number. No, the definition of a second is a certain number of cycles of something, some atomic transition, and then the definition of a meter is the distance light travels in a certain in a second, or in a certain fraction of a second. So to change the speed of light effectively, you can't in some sense, but you could trick yourself into thinking that it happened if you changed all the other constants of nature in such a way that things seemed the same except for these relationships between the number of cycles of some atomic transition and the size of an atom or something like that. Okay, so likewise, you could imagine some conspiratorial change in all of the real constants of nature, the fine structure constant, the mass of the electron, and so forth. that we would call it a change in the Planck constant. There's no reason to expect that happens, so I don't think it's a hot topic in theoretical physics, and there's also no reason to expect that any of those things change either. We are looking for the individual changes in mass of the electron, charge of the electron, things like that, but the limits on them already are pretty good. Casey Mahone says, how important do you think it is to push yourself out of your comfort zone? Part of me wants to relax and enjoy my simple life, but another part says I'm supposed to aim for something bigger. I feel like a hobbit in the Shire, wondering whether it's a quest I'm meant to embark on. For context, I'm in my late 20s, so I wondered if you may have felt similarly at my age. For the last part of the question, I was very lucky in some sense in that I knew what I wanted to do from a very, very young age, right? That I wanted to get a PhD in theoretical physics, think about the universe, and that's what I'm doing now, many, many years later. So I didn't really worry too much about that sort of thing. I knew that I was in the middle of a journey and I was nowhere near the end of it yet. But more generally speaking, many people are not that lucky, and I'm not even sure that I would recommend that you should try to be that lucky, because many people don't discover what it is they really want to do until later, and that's completely fine. There's a balance, I think, between pushing yourself out of your comfort zone and just enjoying the simple life that you have. Neither one of those two are bad things. Enjoying your simple life is good. Pushing out of your comfort zone, also good. I think it's a very highly personal decision how to balance those two things. The only non-trivial thing I can say is, of course, that there's a default of enjoying your simple life and relaxing, right? Pushing yourself out of your comfort zone is something where the rewards to that can be a little bit less tangible, a little bit less obvious and immediate. So it's something where you might have to push yourself to do it and then find that you're very, very happy you did it, right? Speaking of, we were talking about working out at the gym earlier, same exact kind of thing. Like, I might be sitting here going, I don't want to do that. But then once I actually did it, I'm like, ooh, I'm very glad I did that, right? So it's a competition between your present self and your future self. I'm in favor of pushing yourself out of your comfort zone. I enjoy it, but I don't insist that other people enjoy it to the same extent. So you have to pick and choose. That's not a choice that other people can make for you, but you got to keep your options open. Amanda Bradford says, which disciplines or area of study do you not find very interesting? It's a tough one, actually. I thought about it because there's certainly plenty of things I don't find interesting. But as I thought about it, it's more like specific subsets of areas I find uninteresting. Like in most areas I can think of, at least academic areas, I can find some aspect of those areas, history or literature or whatever, that I find really, really interesting. Now, of course, there are non-academic areas. There are sports or leisure time activities that I have zero interest in. But I think that's not what you're asking. You're asking about disciplines or areas of study. So yeah, that's tough for me. I don't want to sound like I'm interested in everything. I'm not even interested in parts of theoretical physics. But I honestly kind of feel like I don't want to make up a couple of them just as examples, because people will inevitably say, I think that these are intrinsically not interesting, rather than me saying that my personal interest does not lie there. So I would say that for evidence for what I think is interesting, look for how I act and how I talk. Look at the things I do talk about. Those are things I do think are interesting. And the other things I think are less interesting. That's the way you can collect evidence for those hypotheses. Jeff B. says, can you give a brief description of the differences between string theory and loop quantum gravity, and do you subscribe more or less to either one? I think they're quite different. Loop quantum gravity is, in some sense, is a very conservative program. It starts with Einstein's classical general relativity theory for space-time. It rewrites it in a certain set of variables, and then it tries to quantize the resulting theory using techniques of quantization that have been around for a long time. And you, of course, immediately run into problems with that, so you try to be clever about getting around them. I would say, honestly, I don't think loop quantum gravity has gotten very far, to be very, very honest. It's a very obvious thing to try. I'm glad that some people are trying to do it. You never know when they might have a breakthrough around the corner. But I would say that things we've learned from not even necessarily string theory, but string theorists, let's put it that way, because string theory is a very different approach where they didn't try to quantize gravity. They were originally trying to understand the strong interactions of particle physics, and they stumbled upon gravity being predicted by this idea that there were strings, quantum strings propagating through a pre-existing space-time, predicted the existence of gravity. So that's already more promising, right? Like if the theory hands you gravity when you weren't even looking for it, that's a promising kind of sign. And they've gone very far. Now, part of why they've gone very far is because a huge amount of brain power has been devoted to thinking about string theory. And they've also hit obstacles, but so far, mostly they've been able to overcome the obstacles. You know, there are extra dimensions of space-time, but they figured out ways to compactify them and so forth. And through all this effort, to finish the sentence I started a minute ago, we've discovered some amazing things. It's all thought experiment things. It's not things that we discovered in a lab, but things like holography and complementarity are two of the most obvious things, which I think are profound features that will probably be part of quantum gravity, even if string theory is not correct. And, you know, the loop quantum gravity people did not discover those things. They can try ex post facto to match them, but, you know, we got to be fair about what happened historically, that those things came out of people who were doing mostly string theory. And so I'm not sure if either one is right. I think that string theory has given us a whole bunch of fascinating results that are very promising to be part of the ultimate theory. Whether or not the ultimate theory looks like string theory or not, I don't know. You know, I think that it pays to be humble a little bit here. You know, we're trying to do something in quantum gravity that we have no right to expect should be easy. You know, when I started in this game, late 80s, early 90s, it was after the first superstring revolution, but before the second superstring revolution. So honestly, a lot of academics, a lot of high-powered physicists were still very skeptical of string theory. You know, they were waiting for really unmistakable experimental prediction. And that's not what happened, but instead what happened was this revolution in understanding non-perturbative effects and dualities and holography in string theory. That was the content of the second superstring revolution, and that was enough to convince a lot of physicists that it was worth doing, worth hiring people, right? I mean, it was in the 90s that really all of your major big shot universities hired all the string theorists that they could find. There's never been an event that made all the big shot universities hire all the quantum gravity people they can find. But we'll see. You know, I think that, what I was trying to say was, back in the 80s, the reason why people started thinking about string theory was not because it was the obvious next thing to think about. It was because two things happened at the same time. Number one, we more or less finished the standard model, right? We discovered the W and Z bosons. We hadn't discovered the top quark or the Higgs boson yet, but everyone expected that we would. So we had a model that fit all the data in terms of experiments. And number two, the first superstring revolution convinced people that maybe this was kind of a peer into a regime of physics that we had no right to think that we would be able to solve so easily. That was the thought in the 1980s. You know, I mean, Ed Witten said it was a piece of 21st century mathematics dropped into the 20th century. Now, it turns out that it's hard to actually connect it to the real world. And I think in retrospect, we should be completely unsurprised by that. If I needed to pick one, I would pick string theory. But as many of you know, I'm not really a bandwagon follower, and there's very, very large numbers of extremely smart people trying to work out string theory, and good for them. I'm glad they're doing it. I'm trying my own little quirky minority point of view on these questions, and I'm happy to be in a much smaller field than that. Joseph Dundee says, how do you know that something which has never been observed is merely very, very improbable rather than impossible? For example, milk and coffee spontaneously unmixing or a brain spontaneously forming in a void. Could there be an upper limit to the improbability of an event? I don't know if there could be an upper limit to the improbability of an event. I mean, maybe there could be if there are literally a finite number of events in the history of the universe, then 1 over that number is an upper limit to the improbability of it. But I don't know if that's true, and we have no way of knowing right now. My general feeling about these kinds of questions is, you know, we'll never know, and it doesn't matter if there's a difference between very, very improbable and impossible. If the very varies are powerful enough, you know, if the chances that in the entire history of the universe, past, present, and future, a certain kind of event happens with probability 10 to the minus a billion, then what's the difference between that and being impossible? We don't need to know the difference between those two things. It's, for all intents and purposes, not going to happen. For milk and coffee spontaneously unmixing or brains spontaneously forming in a void, our current best understanding is those are very, very improbable. They're not impossible. No one says that those are impossible. They're just very, very unlikely. But if they're unlikely enough, you get on with your life. Yurosh says, what is a degree of freedom for physicists? It seems to me that it indicates different things in different subfields. Degree of freedom is just a way of saying something that can happen, something that can change, a quantity that can change. That's what a degree of freedom is. So literally, if you have a single particle in 3 dimensions, it has 6 degrees of freedom because there are 3 numbers that tell you where it is and 3 additional numbers that can tell you how it can move. So the state of the particle is given by those 6 different numbers. That's 6 degrees of freedom. Now, to be fair, we, like you say, like you imply, we don't use it very consistently. So if we have a field theory, like let's say you have a scalar field theory, so that's just one field, one number at every point in space, people will often call that 1 degree of freedom, even though really it's an infinite number of degrees of freedom because it's a different value of the field at every point in space. But the infinity from the number of points in space is taken for granted. And you say it's 1 degree of freedom. You're supposed to figure out that means per point of space. That's why you do have to keep your wits about you a little bit. But that's what it means, something that can change. As opposed to if you have something like Newtonian gravity, okay? In Newtonian gravity, there's no gravitational waves. If you wave the Earth, if you move the Earth, its gravitational field changes, but it changes instantly throughout space. It doesn't propagate out at a speed. So in Newtonian gravity, if you know what the mass is doing of different objects in the universe, you automatically instantly know the gravitational field. That's not true in general relativity. In general relativity, there's a separate thing that can happen. Space-time can oscillate all by itself. So in general relativity, there are degrees of freedom of gravity in empty space. In Newtonian gravity, there are not. There's gravity in empty space, but it is entirely tied to the matter. Therefore, it's not a degree of freedom. It's not a separate thing that can change independently of everything else. Alexandra Bates says, what is the most difficult physics problem you have solved? What made it so difficult? Yeah, I thought about this question, and it's a difficult question to answer because it depends what you mean by difficult. You know, on the one hand, like, what is the most sharp insight that one ever had? What is the aha moment? And honestly, you know, for better or for worse, my most obvious aha moment was back in graduate school. This often happens. But I was working with Eddie Farhi and Alan Guth on, can you make time machines in 3 dimensions? Can you build closed time-like curves in gravity in a world of point particles in 2 dimensions of space and 1 dimension of time? Which is equivalent to a world with cosmic strings that are perfectly in 3 dimensions, that are perfectly straight and parallel to each other. So a cosmic string has a direction in which it's moving, and if it's perfectly straight, then you can ignore that direction. And so 3 dimensions just become 2. The reason why you would care about this weird physical setup is you can solve all the equations exactly. It's a much easier system to look at than real 3-dimensional gravity with black holes or whatever. So we were thinking about that, inspired by work by Richard Gott, who had claimed that you could imagine time machines in these systems. And what we argued is that you could write down, what Gott did was he wrote down a cosmological solution in some sense, a solution to the entire space-time of the universe that did indeed contain closed time-like curves. But what we asked was, could you start in a universe that did not have closed time-like curves in the past and then create them by some dynamical process? And so we wrote one paper where, you know, we just worked hard and banged our heads against it and said, here's some small evidence that you can't. But then we wanted to, you know, go further and like dot all the I's, cross all the T's, and really make a proof. And we really struggled with making this proof. And Alan in particular, did a numerical simulation showing that there's no region of parameter space where it would work, but we still couldn't find a reason why it didn't work. And then I happened to be giving a seminar at the University of Alberta, and I was talking to Don Page, and he mentioned a fact that I didn't know, or maybe I had heard but forgotten, about the Lorentz group in 2 plus 1 dimensions, the Lorentz group, the space of all Lorentz transformations, okay? Namely, that it has a geometry. And the geometry looks like that of a space-time, and the space-time is anti-de Sitter space. These days, anti-de Sitter space is a big deal, but back then, almost no one was familiar with it. So I took that fact, that was it, just that fact, and that was very provocative to me. I was in my stage of my life when geometry and topology were very, very fascinating to me, and I was trying to learn all I could. So I thought about what it meant that the set of Lorentz transformations in 2 plus 1 dimensions looks like anti-de Sitter space. And what I realized on the plane ride home by sketching things is that this answers all of our questions. That if you think about the space of all Lorentz transformations in 3 dimensions as anti-de Sitter space, then you can instantly prove you can't build a time machine without starting with one from simple geometric arguments, drawing lines on pieces of paper. And that was just wonderful. That was, one of those events, like literally on riding the plane back from your seminar, you have the aha moment that solves this problem. And we used that in our follow-up paper. On the other hand, sometimes what do you mean by the most difficult problem is the one you just got to grind through, right? The one where there are no aha moments available and you just have your equations in front of you and it's going to be pages and that's what it's going to be like. And I've had a couple of papers like that also, about the microwave background, about supergravity. I did a bunch of things as a postdoc on dynamically triangulated 2-dimensional gravity that required many pages of algebra and calculus, many little numerical simulations. It was an enormous amount of work, right? And again, you get the answer at the end of the day. It's a little bit less intellectually satisfying than the aha moment, but there is honor in honest work, and I put that in as well. But none of these are really fascinating problems. Like just be more specific, the microwave background thing that we did. This is with my friend Ted Pine, who also trivia. Ted and I wrote this paper on the cosmic microwave background, but Ted is also the musician responsible for the music in the Mindscape podcast at the beginning and the end. His band Euphonic is the band that is playing. So he's the one who lent me the music for the podcast. But he was an expert on perturbation theory in general relativity back when we were both grad students. And so while I was a postdoc, we wrote this paper on second-order gravitational perturbations of the cosmic microwave background. So people had just discovered the anisotropies of the cosmic microwave background, the Kobe satellite, etc. So they'd worked out the predictions, going back to Peebles and other people. And that's why he won the Nobel Prize for what those were supposed to be. And we asked the question, okay, what is the next order effect? What is the higher order in perturbation theory? Now, in fact, the important higher order in perturbation theory terms are not gravitational. They're, the primordial plasma is sloshing around in complicated ways, and that's really what you want to study. But that sounds complicated. So Ted and I just looked at gravity, just looked at the propagation of light from the microwave background surface to today being buffeted about by gravitational perturbations, the gravitational lensing we were referring to earlier. And we worked it all out systematically, and we found that there were, some terms that people had guessed at, and there were some extra terms that people had not guessed at. And we were completely of the opinion that, look, the microwave background was discovered in the 60s. It took 30 years, 25 or 30 years to discover the anisotropies, probably be another 25 years before this is relevant. Sadly, that was more than 25 years ago, so now it's very relevant. And people cite that paper. It was not, the most systematic or useful paper, but it was first to point to certain things. And it was a tremendous amount of algebra, I got to say. Once you get into second-order perturbation theory and general relativity, even if your cites are relatively modest, it's going to be a lot of algebra. There you go. Igor Parshkin says, while doing my undergrad in physics, how much should I allow myself not to understand fully? What I mean is, it often happens that we're learning something as I can learn how to do, but not really sure what I'm doing. But as soon as I start digging, we're off to the next chapter. How much should I let myself go unlearned while moving forward? This is another question of, taste and personal preference here, because certainly to some extent, you should let yourself go unlearned while moving forward. You don't need to master every step before going on to the next one. In fact, it's very often the case that you don't master earlier steps until later you realize, oh, that's why that was important. So, it's very important to kind of remember what the ideas are and where they might be applicable. I sometimes tell the joke that the real reason to take undergraduate physics courses is so that you know where the answers are in the books, so that you go through the textbook and you know where the formula is for the Laplace transform of something or something like that, right? Like you've heard there was an idea and you don't remember, but you sort of remember where it is in the book. That's like the most important thing that you learn in undergraduate physics classes. So it's great to master things, of course. I don't want to say don't do that, but it is not necessarily a disaster if you don't master everything along the way. Now, it can accumulate, right? If you continue not mastering anything, you're going to get in trouble. That's why I can't really give you very specific advice here, but don't panic just because everything is not crystal clear the first time around. Bob Thomason says, among your scientifically oriented podcasting peers, you are much more sympathetic with the current racial justice movement. For example, I can't imagine them having Cornel West on their podcasts. Can you sum up your take on the state of racial justice in America today? So that's asking a lot. My take on the state of racial justice in America. Probably I can't do justice to that one, as it were. But, I don't think it's good, the state of racial justice in America. I don't think it's going out on a limb to say that. Look, I think there's a lot of racism out there. And I think that a lot of the modern realization is that racism can be kind of hidden, but still really impactful. It doesn't need to be blacks cannot drink at this water fountain, right? There are quieter, less obvious ways that policies and personal opinions and personal actions can have devastatingly powerful differential effects on people because of their skin color. I think that's a bad thing, and we should try to fix it. The other thing, of course, is that there are many people who seem to think that the real tragedy is not racism, but being accused of racism. And I don't agree with that. I think that, if racism exists and we're trying to fix it, then certain things are going to be accused as racist, and sometimes they'll go too far, right? Sometimes there will be accusations of racism that are not completely accurate. That you can't make an omelet without breaking some eggs. That doesn't mean it's right. That doesn't mean you shouldn't fix it when that happens or argue against it, etc. But I don't think that the existence of the occasional overreach when fighting racism is really the problem. I think the problem is racism. I think racism is bad. We should get rid of racism. That is my take on the state of racial justice in America today. I'm going to group a couple questions together here. Tyler Whitmer says, how excited are you about getting images and data from the James Webb Space Telescope? And is there anything in particular you're looking forward to learning from it? Kyle Moorer says, with the JWST looking like it will get to L2 successfully and without any issues, what kinds of questions should we be able to answer in the next 10 years with JWST's power? And Jay Affail says, what discoveries are you most excited to see come from the James Webb Space Telescope? So clearly there's some interest out there. I'll be very honest here. What the James Webb Space Telescope is going to do is going to be amazing stuff that doesn't really intersect with my own personal research interests. Cosmology and physics more generally are big fields. People do different kinds of things. What JWST is really optimized for is mostly looking for galaxies very, very far away and other phenomena in the medium-term early universe. So long after the microwave background, but earlier than nearby galaxies. The reason for that is because it's an infrared telescope. So if you have a redshift, then if you have some object that is giving off visible light very far away, it'll be redshifted in the infrared, and JWST can see it. So how galaxies formed, what happened in those early days of the formation history of galaxies is a crucially important question that JWST is really going to go after. As a bonus, it'll be really, really good for exoplanets, both finding them and then investigating them when they're there. So all this stuff is really fascinating and interesting. None of it is what I do for a living. I'm not sure what instrument one could even imagine building that would give great evidence that bears on the questions that I personally am interested in at a research level, which is why I'm thinking about the emergence of space-time and the foundations of quantum mechanics rather than building specific testable models that you can probe in experiments, because I don't know what those experiments would be. So I'm a fan of the JWST as everyone else in the world is, but I have no special research level knowledge of what it's going to do. F sub H says, it seems to me that entropy is something that emerges qualitatively on the macroscopic level, but how should we think about it on the microscopic? For example, we can say that a castle made of sand is more ordered than a pile of sand, but if we think about each individual grain of sand on the micro level, isn't the configuration of the grains of sand that makes up a random pile just as ordered or disordered as the configuration that creates a castle? Sure. Yeah, 100%. There is no reason to think about the concept of entropy on the micro level. Entropy is a macroscopic concept. It's a concept that gains relevance from coarse graining, from thinking about systems from the point of view of incomplete information, that you know some certain features of the system, but nowhere near the whole thing. So I think that's exactly right. That's how entropy works. If you know all of the microdata, there's no reason to ever talk about entropy. Niccolo Paracini says, do you think there's any correlation between the expansion of the universe and the increase in entropy? I mean, there's a correlation. Yes, entropy is increasing and the universe is expanding. That's what a correlation means. Now, probably what you're asking about, is there any causal relationship between them? And the answer there is yes and no. It depends on exactly how you parse that question. The fact that entropy is increasing and the fact that the universe is expanding have no necessary relationship. You could very easily have a collapsing universe, a contracting universe, in which entropy was also increasing. However, it is a feature of our particular universe, rather than the space of all possible universes, that when the universe was smaller, the scale factor was smaller, things were closer together, and the density was higher, the entropy was lower. So that single fact, the initial conditions of the universe, in which the universe was both dense and low entropy, set up simultaneously the fact that the universe is expanding and the fact that entropy is increasing. So it's not that entropy increase drives the expansion or vice versa. They are both driven by these particular initial conditions that we had near the Big Bang. Rob F. says, I've read that there is no arrow of time in fundamental equations of physics, and that the feature that provides the forward arrow of time we observe in the universe is increasing entropy per the second law. My question is, in the extremely distant future, when entropy has effectively reached a maximum and can therefore increase no further, does this mean that time itself will cease or that time itself will cease or will cease to have meaning? No, it does not mean that. What it means is that time will not have an arrow anymore. I've said this in different places in different ways, but you have to distinguish between time as a coordinate on space-time and the arrow of time, which is an important feature of it in our real world, but not a necessary feature just with the concept of time. Again, think about space. There is no arrow of space. If you're out there in the vacuum, all directions look the same. That doesn't mean that space doesn't exist or ceases to have meaning. It just doesn't have an arrow. Time could easily exist and things could change and evolve in a way that wasn't directed overall, and therefore time would have no arrow. So that will be the case when the universe is closer to its equilibrium state. Behzad Mir-Hashem says, do you think that all the various forms of fine-tuning, from the very low entropy of the universe to the relative masses of the up and down quark, can be explained by one principle? Is that the principle that there are many universes and we happen to live in one suitable for life, aka the anthropic principle? It's possible. You know, I think that there are some examples of fine-tuning. So let's put it this way. Fine-tuning can be thought of as, from a physicist's perspective, some parameters are taking on some purportedly special values that could be very different. And why are the values this particular number rather than a more generic number? So you notice that in those words, I never talked about life or complexity or anything like that. That's what physicists mean by fine-tuning. So when physicists say there is a hierarchy problem, the mass of the Higgs boson is fine-tuned. It's much, much lower than its natural value at the Planck scale. Nothing to do with life or anything like that, okay? So what you want to ask for this question, for the anthropic principle, if it works, that is to say, if we are in a kind of universe where it applies, where there are many different conditions in many different places, and therefore there's a selection effect, you would only observe certain kinds of conditions, those that are hospitable to the existence of life, then maybe you can explain some of these apparent physicist fine-tunings by saying that if they weren't fine-tuned, life wouldn't exist. And maybe the masses of the up and down quarks are an example of that. But we think that other fine-tunings exist that are not examples of that. the Higgs boson is an example. We think, and maybe this is not true, but according to our current best guesses, the mass of the Higgs boson could have been way bigger and still life could exist, okay? There's actually debate about this, to be honest, but it is certainly something that is, I think, the conventional view. And what that means is that there's a fine-tuning that is not explained by the anthropic principle. An even better example is the low entropy of the early universe that we just talked about. Now, you need some low entropy for life to exist, but the entropy in the early universe was way, 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 way lower than it needs to be to account for the existence of life. So you need more than simply an anthropic explanation. So even if the anthropic principle works for some things, I think that there are other things which it doesn't help for. So I left out the best example. There's something called the strong CP problem. There's a parameter called theta QCD in the strong interactions, which governs how much violation of CP symmetry you have from the strong interactions. And it's called theta because it's an angle. The physical effects of this number are the same if you change theta by theta goes to theta plus 2 pi, okay, 2 pi radians. And so you would expect, naturally, it's a number between 0 and 2 pi, or maybe between 0 and pi, because the sign doesn't really matter. But we have limits on it. I forget what the current limits are, but it's less than 10 to the minus 9 or something like that. So this number, theta QCD, is much, much smaller than it needs to be. Has zero connection to life. So we need some dynamical or other mechanism to explain that. That's why axions were invented, to explain exactly that problem. Brad Malt says, in the particle at the end of the universe, you explained how the Higgs field gives mass to particles. Since mass must be conserved, does that mean that the Higgs field doesn't change value when the LHC creates a new Higgs boson, or when a Higgs boson decays? And since the mass of an object is the same everywhere, does this mean the Higgs field has the same value everywhere? So last question first. Yes, the Higgs field has the same value everywhere, except for when you make a Higgs boson. So there's a background value that is more or less very, very close to being fixed everywhere. If you start it vibrating, that counts as a Higgs boson, so the value is changing by a little bit, but the Higgs boson decays away in a zeptosecond, which is saying that the energy in those vibrations is being transferred to vibrations in other quantum fields. That is to say, the Higgs is decaying into photons or electrons or what have you. When you make a Higgs boson in the LHC or whatever, you're making one of these localized excitations. You're not changing the overall value of the Higgs boson everywhere. And you're certainly not changing the mass of anything. I mean, you're making a Higgs boson, but electrons elsewhere, other than where you've made the Higgs boson, are unaffected by what you just did. Finally, what I need to say is that mass is not conserved. We've known that mass is not conserved for a long time. Ever since Einstein explained to us E equals mc squared, right? This is how you can make atomic weapons, because you can turn mass into energy using E equals mc squared. It's energy that is conserved, and even energy is not exactly conserved for various subtle reasons in GR and quantum mechanics, but roughly speaking, energy is conserved. And so what happens is when the Higgs boson changes its value from 0 to some non-zero number at the electroweak phase transition, it gives mass to a whole bunch of ambient particles. Those particles gain energy because you're giving them mass, but there's a huge amount of energy locked up in the Higgs field as it's evolving, and that energy is diminishing. So basically, you're just transferring energy from the Higgs field to all the particles all around it. And that's part of the process you need to take into consideration when you study the dynamics of the electroweak phase transition, if that's something you ever want to do. Angelo Ferrari says, are virtual particles really popping in and out of existence and being exchanged by real particles? There's another yes and no kind of answer to the question. Not really is the short answer, because really what's going on are quantum fields. That's always the answer. And forget about something esoteric like black holes or Hawking radiation. That's also true just when particles scatter off of each other. The picture of virtual particles, as invented by Feynman and others, when you draw Feynman diagrams, the virtual particles are the particles that only are on the interior of the Feynman diagram, the particles that do not either come in from the past or go out to the future, but just appear in the interior lines and loops of the diagram. And this is a way, mathematically, of characterizing the effects of the vibrating quantum fields. That's really what's going on in some sense. However, it's a really good picture. It's a really good way of both calculating and thinking about what is going on. That's why I said the answer is sort of yes and no, because it's fine to think about virtual particles doing what we do in the Feynman diagrams. Now, on the third hand, in the vacuum, in empty space, it's kind of not fine to think about the virtual particles popping in and out of existence, because that gives you a bad impression of what's happening. The vacuum quantum state is stationary. The state is the same at every moment of time. It is not evolving in any way. In particular, particles are not there one moment and then there another moment because they've popped in and out of existence. The language of virtual particles popping in and out of existence is just supposed to be a way of giving you intuition for what the quantum state is doing. And in this case, the quantum state is not doing anything, so I wouldn't take that metaphor too seriously in that case. Donald Hawk says, I went to Villanova from 1977 to 1981, and while an atheist, I did enjoy the required religion-related courses. Did you have similar experience while there? Yes, I enjoyed all my religion courses. I think I took 3. I think that was the number of required courses I had to take. There was like an intro course on something about the experience of Christianity or something like that, but it had a really good professor. I was uninterested in the subject matter. Well, actually, that's not true, even at that level. The subject matter is kind of fascinating, I have to say. Christianity, especially early Christianity, and all the different texts and things like that, that when people were arguing about what was supposed to be their doctrine, that stuff is fascinating. When we got to the later stuff, the 20th century stuff, it was a little bit beyond my sphere of caring about, but still, it's always interesting to hear smart people talk about difficult ideas. So that was fun. I took another course on death and dying. That was interesting intrinsically. And there was another course like on hermeneutics in religion, one applying continental philosophy ideas to the ideas of religion. So that was also very interesting, just philosophically speaking. Douglas Albrecht says, could you explain why you were so confident that the wave function is reality rather than just a great tool for explaining it? Confident is always a dangerous word. There's a technical sense of the word confident, which means that I put a high credence on it. There's an informal sense, means that I'm sure it's right, but I'm not sure that it's right. Like any good scientific theory, we do our best, but we always have a chance that we're wrong. So I do think it's probably represents reality more or less faithfully. Why do I think that? Well, because that's a theory that fits all the data and is extraordinarily simple. It's really the simplest theory you can even imagine along these lines. All other theories are more complicated. So I don't see the motivation for trying to do something different. The only motivation I see for trying to do something different is we don't know yet. Let's keep an open mind, which is fine. And people can work on that. In this particular corner of idea space, I just want to work on the thing I think is most likely to be right. Liam McCarty says, Hilbert's sixth problem was to axiomatize physics. In his words, to treat in the same manner by means of axioms those physical sciences in which today's mathematics already plays an important part. As far as I'm aware, this has only been partly achieved, as some parts of physics like quantum field theory have no axiomatic formulation today. Do you think trying to axiomatize physics is a worthwhile pursuit, or is it merely of mathematical interest and irrelevant to physics? I think the important thing to first note here is that we're not even going to succeed in axiomatizing mathematics, which was another big thing that Hilbert cared about. But Kurt Gödel, with Gödel's theorem and other people, showed that this is not going to happen. You're not going to do it. There's always going to be true mathematical statements that you're not going to be able to prove or deduce from axioms. So axiomatizing things has lost some of its luster since Hilbert had these ambitions. I think the better thing to say is you would like your physics theories to be as comprehensive as possible in the sense that we talked about earlier with domains of applicability, and also completely well-formed. Whatever that well-formed formulation might be, whether it's axioms or something else, you want the theories to be clear. You want them to apply everywhere they can. You want them to be coherent, compatible with each other, etc. I mean, that basic program is absolutely crucial, whether or not it takes the form of explicit axioms or not. Dan Inch says, can you give us an update on the cats? Are they both happy? Is Ariel getting a nice drippy shower each morning? Oh, you're asking this at the wrong time, Dan. The cats lead a very, very good life, and they're almost always very happy. And Ariel does get a shower and post-shower lap time every morning. But they just have gone to the vets recently, and we did something just for scheduling purposes we usually don't do, which is that Caliban went to the vet one day. Ariel went one day, and Caliban went on a different day, rather than bringing them together at the same time. And as sometimes happens, Ariel's the more high-strung one. Like Caliban, he's chill. He doesn't really care what's going on. He doesn't want to go to the vet, but if you take him, he's like, okay, here I am at the vet. Here I am back. And Ariel gets really annoyed with us taking her to the vet, and so she got really annoyed when Caliban came back, because he smelled like the vet. He didn't smell like Caliban anymore. And so she was hissing at him, and she didn't want to have anything to do with him. It took a good, 24 hours of coddling them and other kind of strategies to get them to snuggle up together at night as they usually do. But they're back to doing that. So I think that even though there's still some tiny frustrations on evidence, mostly they're pretty happy right now. They're very healthy, cats. They're just going to the vets for checkups. There's nothing wrong with them. Stephen asks, if democracy is the best method we have for addressing the dissatisfactions of the working class, poorer people, why isn't it absolutely necessary when democracy is seriously challenged to advocate for it until it is secure? Then we can turn our advocacy hours to other multifaceted social problems like climate change, bigotries, technical puzzles. All of these problems are hard. They're harder than physics, as noted in the podcast, but we agree that without democracy, they are much harder to solve, no? I get it, and I think I'm pretty much on board with this, which is why I spend a lot more time talking about democracy on my podcast than I otherwise would, than I would have 10 years ago, let us say. Of course, there's a question being begged here about whether or not democracy is the best method we have for addressing the dissatisfactions of the working class. I think it is, but I don't think it's obviously that. Let's put it this way. Democracy has failed to address the dissatisfactions of the working class, or more broadly, to really do as much for the less well-off members of society than it could. I think it's a dramatic failure of our modern democratic system, and that's part of why it's in trouble. It's just not doing what it's supposed to do. Now, I'm completely on board. I'm of the opinion that it can and should and might if we do it correctly. So I'm not using this as an argument against democracy, but as an argument against being complacent. Just because you have democracy, everything should be fine. Okay, but with all that out of the way, what is the amount of effort we should turn to preserving democracy? Should we prioritize it over climate change and things like that? Here, I would say that we should have the ability to do more than one thing at once. We should be able to both walk and chew gum at the same time. We should be able to preserve our democracy and ameliorate climate change and think about the emergence of space-time from quantum mechanics. The important question is, how do you balance the different amounts of effort you put into different things? And there's a complicated thing at the individual level. What are your personal skill sets? What are your personal interests, et cetera? It's a hard question because maybe I just like doing physics more. So I want to think about physics, but it's not going to help me if democracy collapses. So I see an argument that I should work even much harder than I am at preserving democracy. It's frustrating because it's not clear what that work would entail. But the other thing is, and maybe this is even a darker contemplation, the prospect that democracy collapses and in some ways things don't change that much, right? If people just don't care about democracy, you could easily imagine a system which for at least a couple decades, maybe longer than that, power was concentrated in the hands of a small number of people or in some subset of our population anyway, and still life more or less went on. The trains run and you go to school and teach your classes and whatever, and gradually power and wealth and opportunities and dignity become more and more concentrated until people get pissed off and have another revolution or something like that. But we can't imagine that, if democracy falls, it will instantly be like 1984. I think that's maybe the thing that I worry about the most, is that we will lose our democracy and not care, not really be outraged by it nearly as much as we should. So now I'm depressed. So yes, we should fight harder for democracy. That's the lesson. That is absolutely what we should all be thinking about. I agree with that spirit one way or the other. Paul Hess says, why is a wave so concentrated in one specific place that we perceive it as a distinct tiny particle in one place instead of the wave being spread out much more widely through space? I don't know, Paul. How is this question going to help us save democracy? This is now what's in my head. But actually, this is a very good question, because if you think about the Schrödinger equation or other equations of fundamental physics for the waves that we have in quantum field theory, it is very natural that wave-like oscillations in a field want to spread out. If you poke your finger into the surface of a pond, ripples move out in all directions. And so why in the world do particles in the real world have something like a location in space at all, rather than just being spread out all over the place? And actually, I think you could easily take years of quantum mechanics and no one truly answers this question for you. Or, the answer is implicit in many little pieces of things that you learn, and you have to put it together yourself. A huge part is played by the fact that most particles are in the form of atoms, right? A free electron, the wave function of an electron all by itself out there in the world would indeed spread out all over the place. And maybe you wouldn't notice because you don't notice until you measure it, or it gets measured or decohered somehow by interacting with other particles around it, which might happen pretty quickly, actually. But it would, in principle, all by itself, if there's nothing else in the universe, it would just spread out. But an electron that is bound to a proton, its natural wave form are those orbitals that you learned about in high school chemistry, right? They are localized near the proton or near the nucleus in whatever atom they are in. So it is the attraction of the proton that confines the wave function of the electron. And the proton or the nucleus or whatever is a lot heavier, so it spreads out a lot more slowly. That's the other piece of information you would get, but it wouldn't be connected. Heavy things spread out a lot more slowly in terms of the propagation of their wave functions. So once you get to something like the Earth, which is a big, heavy thing, it has a wave function, and the center of mass of that wave function spreads out almost not at all. Not quite not at all, but almost not at all. So once you get to the big macroscopic world, the spreading is just so gradual that you and I don't notice. Sid Huff says, in a graduate course on research methods, which emphasize scientific principles and procedures such as hypothesis generation, data gathering and analysis, and hypothesis testing, occasionally a student would ask whether the curriculum would address other ways of knowing, usually a student from a non-Western or indigenous culture. In your view, do any of these other ways of knowing, whatever that may mean, deserve time and attention in a research methods course? How would you respond to such a questioning student? Well, I'm not exactly sure what course you're talking about, but if the course is called research methods, presumably it's a course on research methods in some particular discipline. I'm sure that there are courses on research methods in economics or computer science or physics or what have you. And those courses will quite rightly focus on the research methods that are actually used in those disciplines, whatever they are. So, there might be other research methods or other ways of knowing. I don't know where you want to draw the boundaries between those, but there is no expectation that a course called Research Methods in Sociology should teach you every possible way of knowing. It should teach you research methods in sociology. As a broader question, the value of other ways of knowing, it's going to depend a lot on the way of knowing that you're talking about. Some of them are going to be nonsense. Some might be very useful. That's an empirical question. Tell me what you've learned to show us what has actually been achieved by this way of knowing, and then we can judge it empirically. That's what I would suggest doing. Pavlos Papageorgiou says, are you confident that physics will find the theory? Or what if we bump into hard dualities? Suppose we end up with multiple conceptually different models that each describe fully and perfectly what we can observe nature doing. That'd be fine. I mean, there's two possible things going on here, and neither one bothers me at all. One is you have multiple conceptually different models that are exactly like you said, describing fully and perfectly what nature does, then they're the same model. I mean, they're just the same thing going on in different language, right? The Hamiltonian versus Lagrangian formulations of classical mechanics are just different languages to describe the same thing. And in that case, who cares? I'm glad that there are multiple models. I think that they're just describing the same stuff using different words. Another possibility, which is more interesting but also doesn't bother me, is that we find that we have a set of models with overlapping but non-equivalent domains of applicability. So this is the case in the domains of applicability discussion we had earlier, where you have two domains of applicability that intersect in a Venn diagram sense. So there's some region where they both apply, but there's also regions where one applies but the other doesn't. And together, these models describe all of nature, okay? That would also not bother me at all. I mean, that would just be, okay, the way that we describe nature is through this set of overlapping models. Who cares? Like, I don't think there's any virtue in saying that I have a single vocabulary that describes everything. What I want to do is describe nature accurately in as wide a domain of applicability as I possibly can. So we're nowhere near any of these becoming realistic questions to worry about, but that would be my feeling at the present moment. Andrew Goldstein says, in the next 2 or 3 decades, could artificial intelligence advance to the point where it explains how living cells emerge from the information encoded in genes, which I consider the quintessential example of emergence? However long it takes, I think it will be defined by the understanding of synthesis and growth, not by reduction and analysis. What do you think? First, a little gloss on emergence. You can hear Caliban in the background. He's meeping. I'm not sure if this is a quintessential example of emergence, because you are precisely doing what I warned against doing in my notion of emergence. You're using emergence as a process that unfolds over time, how living cells emerge from the information encoded in genes. In my way of thinking, there is a level of talking about genes and chemicals and proteins, and another way of talking about cells and organs and organisms, and both of those simultaneously exist. It's not that one turns into the other. They're both simultaneous ways of talking about the same stuff. Now, your question, I mean, there still is a question about how living cells do emerge from the information encoded in genes in that, in the sort of more everyday notion of emergence. Honestly, I don't think that's that hard a problem. It's certainly hard. I don't want to denigrate the work being done by people who think about these questions, but there's no roadblocks there to figuring it out. I don't see a reason to suspect that you would need artificial intelligence to do that. It's a complicated problem because it's right there at the boundary where you have enough atoms and in your molecules to make them complicated, but not so many that you can ignore their individual peculiarities. So it's a rich problem, and there's a lot of subtleties, and it's going to require work, but it's just good old science work. And I think that it's proceeding at a great pace, and so I'm very optimistic that it will happen, that we'll really understand how you go from chemicals to life. And I can't tell you when. Sorry about the next 2 or 3 decades. I'm very, very bad at predicting timescales. That's just a hard thing to do. Frank Lehman says, sorry, I'm laughing at our cat just meowing in the background. Maybe he heard his name being mentioned in the podcast. Frank Lehman says, 15 years ago, I listened to your teaching company lectures on dark matter and dark energy and was amazed by how such a humongous portion of the universe's makeup was A, recently discovered, and B, so deeply mysterious. 15 years later, have physicists made much progress on either front in understanding the dark sector? At the very least, are there hypotheses for what make up dark matter and dark energy you mentioned in 2007 that are now more or less popular or supported? So there hasn't been that much progress. There hasn't been dramatic progress, or you would know, or we'd be talking about it. I mean, the rough picture that I sketched out 15 years ago, where there's dark matter and dark energy, 5% of our universe by mass is ordinary matter, 25% dark matter, 70% dark energy. We don't know what dark matter is, but it's some particle, probably, it could be black holes, but probably particles that interact with each other very weakly and move slowly. We don't know what the dark energy is, but it's probably just vacuum energy, cosmological constant. If it's not, it's some dynamical thing that evolves slowly, okay? That's what we knew 15 years ago, and that's still what we know today. The only progress that's been made has been of a negative variety. You know, we have been looking for small changes in the density of dark energy over time, but haven't found any. So our limits are better now than they were before. We've been looking for dark matter particles, either created in the lab or bumping into particles here on Earth. We haven't seen that either. So our limits are better than they were before. So there's still plenty of phase space out there for models or ideas that we would not have yet noticed. But the truth is we haven't noticed them yet. So, and there's also been more theoretical models for what dark matter and dark energy could be. But, you know, in the absence of experiment, it's hard to really say that any of them is going to really stick its neck up above the others in terms of popularity. Robert Ruxandrescu says, I'm going through the biggest ideas in the universe videos, and I saw that you pause when you're writing something on the virtual blackboard. This tells me that you represent your thoughts and ideas in spoken words in your mental model, but I'm not sure. My question is if this is true, if you're a spoken mental model type of person. There's a famous example by Richard Feynman where he could count in his head and read, but couldn't speak. Whereas a friend of his could count in his head and speak very well, but couldn't read at all. I'm wondering what kind of difference this makes in terms of math, communication skills, and so on. Do you think that you would be a better mathematician if you were a visual person? I think this is a very good question, but actually I don't know that much, even about my own, where I lie on these spectra that you're indicating in this space of possibilities. It is true, I am very bad at talking and writing at the same time, or even talking and drawing at the same time. And, I discover this anew every time I teach a course, but certainly I discovered anew when I did the biggest ideas in the universe videos. So I learned just to mostly shut up while I'm writing on the board. The part of my brain that is writing and the part of my brain that is supposed to be talking are certainly overlapping parts, and they cannot do both at the same time. Likewise, unlike some people, I cannot really listen. If I'm writing, I don't want to be listening to music with lyrics. I don't want to be hearing words anywhere else in the world. If I'm writing, I'm focusing on those words one at a time. And I'm very happy to listen to instrumental music, for example. Now, on the other hand, in the world of mathematics, there's a famous distinction between algebraists and geometers, people who think more in terms of equations or more in terms of figures. And when it comes to math, I'm more in terms of figures kind of guy. I reason much more geometrically than algebraically myself. So I do not have any idea how these different features fit together. I think this is interesting stuff, but I haven't really thought about it that much. Vu Chao says, as a theorist, are you personally excited when your work is confirmed or refuted? We talked a little about this before with general relativity, but obviously my own work, I am most excited when it's confirmed. As part of the scientific community, if you have a theory that's refuted, it makes a big difference whether or not that theory has previously been accepted or not. Like, to have an idea that someone just throws out there without any support yet and then to have it immediately refuted, that's not exciting for anybody, okay? What's exciting is if you have an accepted idea. So you first have it confirmed and you realize, this idea does have some usefulness. And then it's refuted, so you realize, there's a limit to its usefulness. Then both of those are teaching you a tremendous amount. So as an individual, I just want confirmation after confirmation. As a scientist, I want a back and forth between confirmation and refutation. Rob Patro says, you've explained on a number of occasions that Everettian branching happens either instantly or at light speed. Specifically, one can choose how to interpret the branching, since presumably these will be equivalent from the perspective of the observers at the source of the branch. My question relates to how this interpretation interacts with quantum entanglement. If Alice and Bob have entangled particles and travel to a great distance, then Bob observes his particles. How does branching happen? Given that Bob will now know the state of Alice's particle instantaneously, and Alice, when she observes, will know what Bob had observed. So this is exactly why I prefer to think of it in terms of instantaneous branching all over, even though that is contrary to the spirit of special relativity, even though it's completely compatible with the letter of the law, as it were, because it's a completely unobservable effect. If you say that when Bob observes his particle, the branching happens instantly, if you're a many worlds person, then there are now two copies of Alice. There's an Alice in the spin up branch and Alice in the spin down branch, but she doesn't know, because she has no idea that there are now two copies of her, because they're exactly identical copies locally. So one of them will be on the branch that later, when they visit Bob, will see spin up. The other will later visit Bob and see spin down, as everything is perfectly compatible. If you want to believe in the story where the branching sort of spreads out at the speed of light, then you have to have rules when that spreading out branches overlap, how they reconcile with each other, right? So the branch where Alice sees spin up, if the spins are initially counter-aligned, has to have the property that when it joins up with Bob's branches, it joins up with the one where Bob was spin down, etc. So that's complicated, but you can do it. You can work it out. I just think it's a little bit of complication we don't really need. Sandro Stuckey says, is Microsoft real? We're back on this one. I liked the broad stroke of Jody Azuni's account of what is real, but was disappointed in the answer it gave for his concrete example of Microsoft. Now I have to decide which I should trust, his theory or my intuition. How does one evaluate a philosophical theory like nominalism? So this is why I wanted to get to this last question here. You can have your own. I already discussed that I think that it's okay to say Microsoft exists in a certain sense. I can sue it. Right? I mean, it must exist. I can interact with it causally, okay? But okay, I get that it's a slightly different kind of existence. That's okay in my mind. But then this question, how does one evaluate a philosophical theory like nominalism? That's a more interesting one, because on the one hand, I do think it's important. I think it's not beside the point where you stand on these issues. On the other hand, one could take a stance that says it just doesn't matter what I think about things like this. And so I think it does matter, but I think the mattering is indirect. Simply having a stance about whether or not Microsoft is real or not real at a philosophical level, I mean, if you act in exactly the same way, you might say that it doesn't matter. But I think that that stance would affect how you act ultimately, how you think about these things, and also the natural numbers, or other mathematical concepts. That's really where I think that's where nominalism kicks in and has some oomph, where it says that numbers don't have independent existence other than a way of talking about the physical world. I think that your attitude towards questions like that changes how you move forward, changes how you develop further theories, right? We're not static in our understanding of how reality works. We're trying to improve it. And as you can tell from different scientists talking to each other in different ways, different people have different ideas about the best way to improve our current understanding. Why? Why do they have different ideas about the best way to improve our current understanding? Why can't everyone just agree with that? And part of it is because they have different intuitions about things like this. I'm thinking about how to build a completely finite quantum mechanical model, because that would potentially have different ramifications for your idea about mathematical Platonism. So it's literally the case that a stance towards mathematical realism is affecting the research work that I do in that case. So that's why I think it's important, not because you're going to make some different prediction for some scattering experiment at the LHC, but it changes how you think about the universe and therefore how you go about being a theoretical physicist. And even though some of us get paid to do it, we are all theoretical physicists at some level. We are all developing theories about the world and using those theories to get through the day. So it's something that matters for everybody. John Stout says, forces are mediated by W and Z bosons, gluons, possibly gravitons, and photons mediate electromagnetism. But the way we generate electrical power in magnetism is to move electrons. So it would seem that electrons would mediate electromagnetism. Can you explain how photons do when we are talking? I think you mean what photons do when we're talking about electricity and magnetism. Yes. So electrical charge is carried by electrons. It is not carried by photons. So electricity and electrical power come about because we move charges around. And so electrons play a crucial role in doing that. But the forces that accelerate those electrons, right? F equals ma, force is mass times acceleration. If the electron is accelerating to go from being stationary to being moving in a power wire, why is it doing that? The answer is because of photons, or more broadly, because of the electromagnetic fields, right? That the photons are excitations of. So it really is the electromagnetic field that provides what we call the force. Of course, I can say this also, that the whole separation of things into, particles and forces is a little bit old-fashioned. As I've just said a little while ago, it's all quantum fields interacting with each other. That's all that matters at the end of the day. And whether you want to call one a force, one a particle, or whatever is kind of up to you in some sense. Alex Siegel says, according to my understanding of the holographic principle, the maximal entropy in a region scales with the radius squared, or the surface area of that region. In other words, the density or average of the maximal entropy scales with 2/3 of the power of the total. For extremely large volumes, this density would be quite low. Could this explain the expansion of the universe? The entropy of the universe is ever increasing, so the volume must go to make room for the entropy. I was with you there for a while. Like your statements about the holographic principle, etc., are completely correct. Could it explain the expansion of the universe? No. It has nothing to do with the expansion of the universe or with the increase of entropy of the universe. Because the expansion of the universe doesn't need explaining. We know the explanation of it. We have Einstein's equation. We have cosmology. We have the Friedmann equation in cosmology. The universe expands because there's a relationship between energy density and the curvature of spacetime. And the expansion of the universe is one version of the curvature of spacetime. So if there is matter and energy in the universe, it must either expand or contract or be very, very delicately balanced on a hilltop in between, but that's unstable, as we learned a long time ago. So we don't need an explanation for that. And in fact, if you continue on, as we talked a little bit earlier in this very long AMA podcast about the eventual equilibration of the universe into a de Sitter phase where there's no stars or galaxies hanging around, just empty space with a positive cosmological constant, the horizon size around a point will asymptote to a fixed number. It will not continue to grow. So the entropy inside that horizon size will stay fixed, but the universe is still expanding in some very real sense overall. That's what de Sitter space does. So it's not really a connection there, as you might have guessed. Phil says, could you give a rough explanation of how spin arises from unifying special relativity and quantum mechanics? Don't be afraid to be a bit technical in your answer. Actually, I think it's easy to give a accurate answer because it doesn't arise from unifying special relativity and quantum mechanics. It's perfectly okay to have spin in non-relativistic quantum mechanics. In fact, usually when we first encounter spin in quantum mechanics, it's in the context of a non-relativistic theory. A single spin 1/2 particle, a single qubit, right, is something we can easily talk about in non-relativistic QM. I think what you're referring to is the fact that when we do relativistic quantum mechanics, we, for reasons that we talked about already earlier in the podcast, we immediately go to field theory. And there, in the context of field theory, it is sensible to be a little bit more systematic about how to implement the symmetries of Lorentz invariance, rotational invariance, boosts, and translations, and all that, the whole Poincare group, as we call it, of symmetries. So you look at all the different representations of these symmetry groups, and you find they fall into different classifications, and the different classifications have different spins. So spin sort of arises from this attempt to be systematic. But it also would have arisen from an attempt to be systematic in non-relativistic quantum mechanics. If you had just had the Galilean symmetries that included rotations, you would also have found representations that include spin 1/2 particles and spin 1 particles and so forth. So I don't really think that there's any necessary connection there. Christopher Matthews says, if we are going to finally achieve the theory of everything in the foreseeable future, do you think the major breakthrough will come from the theoretical side or from the experimental side? Obviously the answer is I don't know. We don't know, right? Predicting the future of major breakthroughs is a difficult thing to do. It could come either way, honestly. I think that right now there are no experiments that are being done which have the character that if they get a certain result, that will give us a huge clue about what the theory of everything is. And if they get another result, we won't. If the LHC somehow finds a whole bunch of supersymmetric particles or something like that, that would count as evidence in a certain direction. It still wouldn't be definitive. For example, you can have supersymmetry even though string theory is wrong, right? So it's not like close to homing in on a theory of everything, but it might point us in a certain kind of direction. But we have already turned on the LHC, and the easy chances for finding supersymmetry have not panned out. So therefore, it doesn't seem like the best way to bet right now. I think back before the LHC, I recently looked back at my predictions blog post for the LHC, and I put a 60% chance on finding supersymmetry. So yeah, that was sort of hedging my bets, right? 60% is almost 50%, which almost means you have no idea. But I only put a 3% chance on finding the Higgs boson and nothing else, which seems to be the way things are going so far. So I'm still hopeful they find something, so I don't be put in the situation of having my 3% chance come out right. Depthi Amasurya says, when we talk about the cosmological events, we use timescales such as 10 to the minus 33 seconds after the Big Bang. What is the justification for using what appears to be a universal time clock for such phenomena? Well, justification is twofold. Number one, the Big Bang, even though it doesn't exist, the Big Bang is just a singularity in the equations, indicating that you need to do better. But in classical general relativity, there is something called the Big Bang, which is a moment in time, right? So it is a starting moment. So it provides a beginning for your clocks. And number two, cosmologically, there is a rest frame, right? I know in relativity, there's no preferred rest frame in space-time. But when you have space-time plus matter and energy, like you have here on Earth, there are rest frames that are kind of better, or at least more obvious to use, more natural than others. Here on Earth, it makes sense that we measure the speed of moving vehicles with respect to the ground rather than respect to the sun or something like that. Likewise, in the universe, there is a rest frame given by the rest energies and velocities of particles in the universe. If you're standing at some point in the early universe, you will either be at rest or at motion with respect to the surrounding plasma of particles. So in that rest frame, there is a natural way to calculate time. Calculate the time of a particle that is at rest in that rest frame. And that's what you do. That's today, the rest frame that is at rest with respect to galaxies and stars and things like that. So there's a natural clock to use, and it's more or less universal. Wesley Clare says, when making personal decisions, do you actually calculate your credence? For example, how to weigh different consumer products, how to spend leisure time, etc. No, implicitly I do. I mean, I certainly do in scientific contexts, but in personal decision contexts, I don't usually, it's not really a matter of comparing different expected values because there's not a lot of randomness in the calculation, right? If I'm saying like, do I want to have pizza tonight or Chinese food? It's not like, well, there's a 50% chance that pizza will make me happy or whatever. I know more or less, I can accurately predict how happy the pizza will make me, how happy the Chinese food will make me. So credences don't usually come in to the calculation, but in some cases, they're definitely there in the background. Alexander Rowe says, how accurate can physics be described without using the equations? It's hard to say exactly because it depends on what you mean. Any equation can just be translated into words, right? The Einstein tensor is proportional to the energy momentum tensor, and the constant of proportionality is 8 pi g. There, that is a sentence, but it contains exactly the content of Einstein's equation of general relativity. And I could even attach vocabulary words to express what I mean by the Einstein tensor and the energy momentum tensor. So I think maybe what you mean is how accurate an idea can you get about what physics is saying without referring to the specific quantitative relations that we call the laws of physics, right? So the comparing Einstein's equation, whether it's in symbolic form or verbal form, to a sentence of the form, the curvature of space-time is caused by energy and momentum, something like that. And, I think you can go pretty far understanding the principles of physics just on the basis of those verbal descriptions, but you're always missing something, especially because it's not because saying that the curvature of space-time is caused by energy is not including the particular quantitative value of the coefficient, right? That's not the problem. The problem is that if all you have are those words and you have no idea what the mathematical concepts are, then you don't really know what is meant by the phrase the curvature of space-time. Because in Einstein's equation, the curvature of space-time that matters is a particular representation of it, a particular characterization of the curvature called the Einstein tensor. There's other features of the curvature of space-time that are not included in the Einstein tensor, that are irrelevant to it, etc. There are other ways of thinking about the curvature of space-time. So that verbal expression is just incomplete. It's not the whole story. It doesn't tell you everything. So unless you really are going to put in the effort to understand the concepts behind the equations, you can get a rough idea of what physics is saying, but not a very accurate idea, I would say. So I think that's a big part of the motivation behind the biggest ideas in the universe. Like I said, I'm not teaching you how to be a physicist in these books. I'm not teaching you how to manipulate the equations, but I want you to understand the equations well enough to really appreciate what it means to say the curvature of space-time is driven by matter and energy. I think if you read the book, you really will be able to understand what that means, even if you're not a physicist yourself. Jeffrey Siegel says, do you think the Republican Party can survive the damage to their moral authority due to their bald-faced lies and attempts to undermine the electoral process? Or conversely, do you think the country can survive if such a Republican Party is successful in taking the House and Senate in the midterms and the presidency in 2024? Since you're phrasing the question in terms of can the Republican Party survive, yeah, 100%. I have no doubt that it can survive. That's different than will it survive. These political questions should never be thought of as absolutes. Oh, this can't happen if this goes this way. You can be surprised. Social systems, we can be surprised. I can be surprised. Social systems are complex, multi-causal, and hard to predict. So I could easily see a future in which the Republican Party, devotes itself to lying and undermining the electoral process and fails, and yet just keeps trying for a long time. Or maybe it keeps trying for a while, it fails, and therefore it switches its strategy to something else. Or it succeeds, right? And it succeeds and it changes the rules of voting and representation so that it just keeps succeeding. It builds in its own success strategies, and then it just perpetuates for a very long time. And the country can survive likewise. I mean, like I said before, there's sort of a nightmare scenario where we have a failure of democracy and people are happy with that, right? And the Republicans are just ruling for the next 100 years. These are all plausible scenarios for the future. We can debate the relative likelihood of them, and we can debate how seriously to take them and what to do about them. But there's no doubt that they're possibilities. I think it's just a huge mistake whenever you're thinking about politics or future history to think that you know better than you really do, that things are absolutely likely or impossible or what have you. I like to keep a very, very open mind when it comes to planning for the future in these political questions. Jordan Williams says, I often describe myself as a hardcore atheist and find religions, especially the monotheistic deities, primitive relics. However, on another level, it seems coincidental that quarks and electrons have somehow organized themselves into conscious beings, ultimately the universe theorizing about itself. Does it seem possible or likely that there's some sort of mind, very loosely defined, behind our comprehension at work? So first, I think it's very interesting that you think that the monotheistic deities are especially primitive relics. So presumably the pantheistic deities, polytheistic deities are less primitive. I don't know. That's a different take. I'm not sure you wanted to say that, but it's a defensible take. And secondly, no, I don't think it is likely in any sense that there's a mind behind the ability of we human beings to be conscious and aware, even though we're just made out of quarks and electrons. To me, that's just the lesson of what we've learned about emergence and complexity, that you can have very, very simple underlying pieces organized themselves in some sense, just under the mindless, purposeless working out of physical laws into very complicated information processing systems. There seems to be no difficulty in having that happen. Of course, there's lots of difficulties in figuring out the specific things that did happen in human history. So that's, plenty of work to be done, but I see no obstacles to make me say, well, this can't work. We got to think outside the box and imagine that there's some mind behind it all. Now, you do say, does it seem possible or likely? Those are two very, very different questions. Does it seem possible or likely? It's not likely, but I think it's certainly possible. Sure, it's absolutely possible. You're welcome to contemplate that possibility. Brian Tidmore says, in Good Will Hunting, assuming you've seen the movie, there's a scene in which Matt Damon burns what could be a mathematical proof. As it burns, he says it's not his fault that he was born with the ability to understand that level of math. Is there any truth to this idea that some people have brains capable of higher computational understanding than others? Are there any quantum theories that you yourself are unable to comprehend? Taking the last question first, there's certainly quantum theories that I don't comprehend because there's a lot of quantum theories out there, a lot of models of different things in field theory and condensed matter physics and in other areas of physics. I'm not trying to comprehend them. It's not like I've tried and failed. Are there any that even if I really, really tried and put my brain to it, I would fail to comprehend? Maybe. I don't know. I doubt it, honestly, because, these are made up by other human beings and they did the hard work in making them up. Once they're made up, I can really sit down and try to comprehend them. I don't think that's really a stumbling block there. about human brains, it seems pretty likely that some are more powerful than others, just very naturally, right? Some people are taller than others. Some people have different hair color than others. People are different, and their brains should be different also. That makes perfect sense to me. But I do think that we are often far too quick to jump from that very anodyne statement, human beings are different from each other, to some determinism or some almost magical power that, some people do math and some people don't, right? Some people can just see the math without really even trying very hard. Now, there are stories out there of savants in mathematics that just, see a math problem and solve it in their brains. But for the overwhelming majority of cases, including super genius mathematicians, what you're actually seeing is the result of a lot of hard work. Even the best mathematicians out there have to work really, really hard to understand what's going on, to think about proving new theorems and so forth. And what you see is the final product, and it can look miraculous. And therefore, when Hollywood portrays it, they portray it as miraculous, but really there's a lot of work going on that would not make good cinema, but it is the bread and butter of making progress in these areas. Carlos Nunez says, is there any movie that you've watched several times? Yeah. I mean, sure. Look, I was 11 or 12 years old when Star Wars came out. I was the target audience for the first movie ever where people just kept going back over and over again to see it. And I was definitely among those people. I saw it maybe like 3 times at the time, not 20 times like some people did. But, that was definitely part of the experience. Raiders of the Lost Ark, likewise, etc. And, more in my maturity, as it were, there are definitely movies that I think are favorites and I'm happy to watch over and over again, whether it's, old classics like Casablanca or newer ones like Brazil that I can just enjoy many, many times. And, I don't mind. I watch movies on TV mostly now, right? Especially because there's a pandemic, etc. So if there's a movie, I'm sure I've watched the Harry Potter movies several times just because sometimes they're on TV in the background. I mentioned earlier in the podcast that I cannot write when there are spoken words going on, whether it's music with lyrics or TV or talk shows or podcasts or whatever. I need no words around me. My wife, Jennifer, is very different. She loves to have sort of things that she's already seen on TV in the background while she is writing, whether it's, Midsummer Murders or Harry Potter movies or whatever. So just one way or the other, you're going to see a lot of movies several times. Louis B. says, can you put cream into your coffee without thinking about the universe? No, I cannot. Happily, number one, I don't put cream into my coffee. I drink coffee a lot, but it's always black. And number two, I can never stop thinking about the universe. The universe is all around us. You should be thinking about it all the time. At least I know I am. Napoleon's Corporal says, on several past episodes, the subject of misinformation and how it spreads has come up. Can opinion, when clearly identified as such, ever be deemed to be misinformation? And can it ever be right to suppress or censor it? I think the simple answer is that no, opinions are not misinformation and they generally should not be suppressed. The only hesitation I have here is you're putting the word ever in there twice. And I don't think these are questions about which we should be absolutist. I think it's a mistake. I think it's exactly that clarity of values trap that Tin Wen warned us about. Don't, think about what is happening here. The question is not, let's invent some principle that is absolute and can never be violated. The question is, what's the best thing to do in this complicated situation? I am overall, my impulses are let people have whatever opinions they want and spread them however they want. And hopefully better opinions will fight back against them. But I can imagine there are counter examples, that there are cases where doing that would be really bad. I don't have a complete theory of that. That's why I'm a physicist, not a legislator. I think it's an interesting question, an important question. But even if my inclination is let everyone say and think whatever they want, I'm very open to the possibility that there can be circumstances under which that's not a good idea. Murray Cantor says, I am a good Bayesian, however this conundrum is a bit puzzling. We are supposed to update our beliefs based on the evidence. Doesn't that assume we're 100% confident in the evidence? If not, do we have to account for the uncertainty of the evidence and look for evidence of the truth of the evidence? This seems to lead to some infinite applications of Bayesian rule. Has this ever been addressed? Well, I'm sure it has been addressed, but I think that it doesn't necessarily lead to an infinite application. I think you just have to be aware that what you are perceiving does not necessarily map directly onto reality. Okay. And this is always good advice. So if I think that I am seeing a picture of a duck in front of me, I should be aware maybe I'm not seeing that. Maybe my brain is being tricked. Maybe I'm hallucinating. Maybe I'm just making a mistake. Maybe it's an optical illusion. Those should be part of my credences. And so your interpretation of the evidence you get as something is happening in the world should always come with some error bars, with some uncertainties attached to it. But once you attach those uncertainties for some good reason, I don't think you need to attach uncertainties to the uncertainties and uncertainties to the uncertainties of the uncertainties, etc. You can stop once you have the uncertainties attached to your evidence and your likelihood functions and so forth. DLP says, do you think ethical arguments work the same way that mathematical proofs do, just starting from different axioms and concerning different entities? Or are there logical steps that are valid in one but not the other? I think it's basically the same idea, in the sense that I think that mathematical proofs are just a subset of logical arguments, right? Deductions of conclusions from starting points or from agreed upon things about the world. It's not the only kind of reasoning that we can do out there in the world. Science is a little bit different, but it can still be put into the same broad category, right? In science, we don't have axioms that we hold to be 100% reliable. We do our best to get the best explanation of a set of complicated pieces of data that we can, and there's always some error bars, some probability that we're wrong and so forth. But nevertheless, within science, we use deductive reasoning, logic, in the same way we use it in mathematics. I'd say the same thing about ethical arguments. We might have starting points that we either agree on or don't. But once you agree on your principles, if that's how you're reasoning, if you have some principles or you have some starting points, then you use the rules of logic to derive conclusions from there. Yeah, I can hardly imagine another way to do it. I'm not sure. So in other words, I think that if people think that they're doing something different, it's just a different sort of presentation of the same thing. Logic is more or less logic. Now, again, as I'm saying that out loud, all of the footnotes are coming to my mind. There are different systems of logic. I mean, at the very basic level, there's propositional logic, first order logic, second order logic, but there's also subcategories within all of those. And you can actually, there's modal logic, for example, and you can potentially either reach different conclusions or be able to reach conclusions or not, depending on what system of logic you are using. Those are fair enough technical worries that I think don't usually matter for down-to-earth ethical questions. So I think that, roughly speaking, what I said originally is right. You just use logic in the same way in ethics as everywhere else, with the footnote that using logic is not quite as simple as we might think if all we did was to take a single, lecture in logic or something when we were in high school. Hilbert Spaceman says, given that 2- and 3-dimensional Euclidean spaces have very different properties from each other, what do you see as the utility of physical theories in lower dimensions? Well, it depends on the physical theory. Sometimes it's much easier to solve the equations in 2 or 3 dimensions, right? Or two spatial dimensions rather than 3, or even 1 spatial dimensions. And even being able to solve the equations in an unrealistic situation might give you some insight if you were instead just forcing yourself to always look at the realistic situation, but one where you could never solve the equations. So there's a classic example earlier in the podcast when I mentioned looking at the creation of closed time-like curves, time machines, in 2 + 1 dimensional gravity, so 3 space-time dimensions. Incredibly unrealistic. There are different properties of gravity in 3 dimensions versus 4 dimensions, but you still learn something. You still learn something that you might not have known because the answers that we got from our theorizing were highly non-intuitive. You wouldn't have guessed them. You had to actually go through the work to get there. And from that answer, from that non-intuitive answer, you can be inspired to get some conjectures that might apply to the real 3 + 1 dimensional world. That happens over and over again. The other reason, of course, is that there are plenty of physical, real cases where, for all intents and purposes, the problem that you're looking at really is just two spatial dimensions or even one spatial dimensions. We talked earlier in the podcast about electricity going down wires. For a very, very good level of approximation, you can treat that as a one-dimensional problem, the direction along the wire. There are plenty of condensed matter systems that are two-dimensional, superconductors or, sheets of graphene or something like that. So even though there are three dimensions of space around us, that doesn't mean that they're all being accessed by some physical system. In that case, studying numbers of dimensions makes perfect sense. Josh Bauer says, in the field of software engineering, there are several layers of abstraction at which you can think, while ignoring the details of the lower levels. For example, when thinking about writing code, you can ignore what circuits will actually do when it's executing. This is by design. It enables the creation of complex systems. This strikes me as designed emergence. Do you think studies of emergence can learn anything from the engineered abstraction layers in software? I mean, at that level of question, it's always possible. Sure, maybe. It is an example. I agree that there's absolutely a close resemblance of what you're describing to what we've been talking about earlier in the podcast about emergence. On the other hand, the reason I'm hesitating a little bit is that one of the salient features of the emergence of complex systems, or even just higher level systems generally in the real world, is that they are not designed. And there are differences between designed things and non-designed things. Just look at a car versus a cow. They're about the same size, but very, very different things going on. They both move, but they move using very different methods of locomotion. They're both powered by fuel, but the fuel they use is very, very different. They can both be damaged, but what happens when they're damaged is completely different, and so forth. For very good reasons, because the car has to be held in the mind of the engineer of the car, or at least, pieces of it do, and then the car as a whole is held in the mind of some boss engineer. The cow doesn't, right? The cow can be infinitely more complex than the car can, really, when you get down to the detailed level. The other thing is that the cow is not designed for any purpose. The cow is just finding its niche in the ecology, whereas there was a reason why the car was designed. So the design of a car comes from somebody thinking about the future. They say, what will be the need that is served by me building this? The design of the cow has nothing to do with planning for the future, okay? It's always what has served, just trying different things out randomly. That's what natural selection does. And in the current moment, asking what works. And if it works, you reproduce and send that on to the future generations. So, a biological organism will generally be much more flexible and multi-purpose than a technological designed organism will be, because it wasn't designed for any purpose. So it will typically be much more robust. Biological organisms are much better at repairing themselves than most machines are. On the other hand, a purpose-built machine for one purpose will generally be enormously better at that purpose than a biological organism will be. Cheetahs go very fast, nowhere near as fast as the fastest car or the fastest rocket ship, right? We're better at doing specific goals by engineering than biology ever is. So I think that even though it's not a necessary fact, as a matter of practice, there are differences in the styles of higher level behavior you get and the relationship to lower levels that arise out of intelligently designed emergent systems versus undesigned systems. Oleg Ruvinsky says, can you please explain the idea of time reversal symmetry, how it relates to the arrow of time, and how we should think about it? Time reversal symmetry is just the idea that, given some laws of physics, and if the laws of physics are the following form, you give me the state of a system at one moment of time, and the state includes, in Newtonian mechanics, both the positions and the momenta of all the different parts of the system. In quantum mechanics, it would just be the wave function of the system. And then the laws of physics tell you how to evolve it forward in time. You can also evolve it backward in time. That's called reversibility. That's not time reversal symmetry. Reversibility says that the amount of information you have in the state of the system is the same from moment to moment. So there's a unique map from one moment of time to the next, and you can go forward or backward using that map. That's reversibility. Time reversal invariance is that given the state of the system, there's something I can do to that state, some way that I can change it. In particular, in the case of Newtonian mechanics, that way would be reverse all the momenta. And then once I've done that, I can run the system backward in time, and it would undo the evolution it would have done forward in time. So if you like, time reversal symmetry says, take the state now, evolve it forward in time a little bit, time reverse it, which means flip all the momenta. And in quantum mechanics, you do other things, but classically you would flip all the momenta. Then evolve that backward in time. And the claim is you would get to the same state you started in. Sorry, you have to undo the time reversal. You have to undo the momentum flipping. That's time reversal invariance. And so in quantum field theory, time reversal invariance is violated. In the standard model of particle physics, you can do experiments that show that doesn't quite work. Except there's a footnote here that what do you mean by time reversal symmetry? So reversibility was very clear, right? The information is conserved from moment to moment. The definition I gave of time reversal symmetry was a little more loosey-goosey because I say, evolve forward in time and then do something to the state. In particular, change the direction of all the motions of the particles. But in quantum mechanics, it's a little more subtle. And then you can go backward. And so the question becomes, is there always something you can do to the state so that you could reverse it in time and get back to where you started? Is that necessarily true? And the answer is, and I don't think this is well appreciated, I started writing a paper about this at one point, but then got distracted by other things. The answer is, it's an unsurprising answer, which is why I'm not motivated to write the paper, but if your theory is reversible, if it has the property that the information in the state deterministically is carried from moment to moment in time and can go either forward or backward, then there is always a set of things you can do to the state that you can call time reversal that will be a symmetry of the system. So that's clearly true for Newtonian mechanics. How do you reconcile it with the claim that I just made that in particle physics, time reversal symmetry is broken? Well, it's because particle physicists have chosen to define time reversal symmetry badly. Or not badly, but they've chosen a particular definition of what they mean that turns out to not work for actually reversing the system. Now, if you're worried that I'm making an overly strong claim, there is another symmetry called CPT, which means charge conjugation, parity reversal, and time reversal. Parity reversal is changing directions of space rather than time, so that's not very hard. Charge conjugation is basically exchanging particles for antiparticles. And CPT is conserved in the standard model of particle physics. Indeed, it needs to be conserved in any local Lorentz invariant quantum field theory. So what you could do, and this is all in my brain because I literally wrote about it in my book that is going to be coming out in September in the Biggest Ideas book. You could just define CPT to be what you meant by time reversal invariance. You could just define T prime equals CPT. And that is a time reversal invariance symmetry that is absolutely conserved in the standard model because it has to be something. There has to be such a symmetry because the underlying dynamical equations are completely reversible. And therefore, to get to your actual question, well, how does it relate to the arrow of time? It doesn't. It doesn't relate to it at all. The arrow of time is a macroscopic phenomenon that comes about from the fact that entropy is increasing in the universe, has nothing to do with time reversal symmetry. It has a lot to do with reversibility, and reversibility, if it's there, always implies time reversal symmetry. But the real world has the feature that the microscopic equations seem to be reversible. The macroscopic world doesn't. And that's where the arrow of time seems to come from in our real world. So it's just unrelated to time reversal symmetry. Cooper says, are there a significant number of physicists that enjoy visual astronomy as a hobby? For me, it is good for my soul to directly see other galaxies with just my eyes and some mirrors in my backyard. I wouldn't say significant numbers, honestly. There's absolutely numbers. I was a astronomy major as an undergraduate, so I definitely did quite a bit of stargazing through pretty good telescopes. But as a kid, that was never my thing. I was a theoretically inclined guy, even as a youngster. But I've had my own graduate students or my own colleagues who are very, very interested in that. And so, but still it's a minority, I think, of them. So, visual astronomy is a wonderful thing, like being able to see the sky with your eyeballs, even if you get a bit of a help from some telescope that you're carrying on your back or carrying in your truck or whatever. It's still pretty amazing because, it's kind of interesting. There's a interesting feature of the world that our sky is not that interesting. I mean, it's pretty interesting. The sky at the level of our naked eye, if you're really out there in a dark place and you can see the Milky Way in all of its glory and so forth, the Milky Way is pretty awesome. Okay, that's the Milky Way, not just as a galaxy, but as a visual sight is pretty amazing. But stars are not that amazing. They're just literally points of light. I mean, we know that they're very, very interesting close up and when you can see them. And there's planetary systems and nebulae and so forth, but you need telescopes to see all of that stuff. That's an interesting fact about the universe, that there's a lot of interestingness out there, but it's far enough away that we can't see it with our naked eye. But it's right on the edge so that if you bring a little telescope that is not that big, you can see some of that stuff. So I think that's just really amazing that little bit of technological boost gives us a qualitatively different view of the universe. And so I think there's a lot of joy that one can get out of that. Having said that, I don't do it myself these days as part of my life. Okay, and on a similar note, the final question of today's AMA is from Matthew McKeever, who says, "What are your guilty pleasures? And how would you even define guilt in this context? I'm thinking about enjoying devoting some amount of time and energy to something others would think trivial, perhaps mechanical watches or automobiles, if you enjoy craftsmanship and mechanical technology, for examples." Yeah, I would push back on the word guilty. I don't think that you should be guilty about your pleasures. Just enjoy your pleasures as long as you're not hurting anybody else. So I'm not that guilty about my pleasures. I'm in favor of pleasures as a general rule. People should have more of them. And presciently, you put your finger on one of my main pleasures, guilty or not, which is mechanical watches. 10 years ago, I had no interest in mechanical watches. I was happy to wear a cheap electronic watch. But then I wrote a book called From Eternity to Here, The Quest for the Ultimate Theory of Time. And it was mostly about the entropy and the arrow of time and a little bit about space-time and time reversibility, as we've been talking about, stuff like that. But, it was my first trade book. I was very enthusiastic about writing absolutely everything that could be thought of and said about this topic. So I did a little bit about timekeeping in the book. And I started reading up about escapements and things like that. And somehow I actually got started reading about the quartz crisis in Swiss mechanical watches. For those of you who don't know, it used to be that mechanical watches were the only watches. Those are what you had. And then in the late 60s, in the 1970s, they invented quartz watches, which are much cheaper and more accurate, right? So that's a win-win, okay? And to a large extent, the Swiss mechanical watch industry cratered. The quartz crisis, it's called, because why would you spend more money on a watch that is not as accurate? And finally, they figured out a reason to stay alive. And the reason was that it's kind of nice to have an elegant mechanical machine on your wrist that serves both as a technological marvel and as a work of art, as a little bit of jewelry, right? Men don't get to wear jewelry. They don't get to adorn themselves with accessories that often, but watches are one way that you can do it. So these days, there's a whole mechanical watch industry, and the price points go from $100 to $1 million, more than $1 million for the super expensive watches. And they really are technologically quite impressive. Many of them, depending on how much you're willing to spend, they're mass produced. But at the higher levels of paying, you're looking at things that get a lot of individual human attention along the way. Some of them are very interesting in their designs, and some of them are beautiful, and some of them are just kind of like rugged and manly, or elegant and artistic and beautiful. And so it's a wonderful hobby to kind of get lost in. In fact, it's a very, very dangerous hobby because however much money you want to spend, you can. So you have to keep that under control. Happily for me, I'm not really a spendthrift. I'm not really, someone to spend more money than I have or want to feel comfortable spending. So I'm not in danger of, buying $100,000 watches, even if I could. I don't think I ever could. good. Could you ever buy? I know people do, but like, could you walk around with $100,000 watch in your hand, worried that like it might break? I don't know. I don't think I could ever be rich enough to enjoy that. But I like the level of spending that I can do on it. I try to restrain myself from buying too many watches. I went through a phase early, like where you buy a lot of cheap watches because you just want variety. And now I realize it's better to save your money, get a nice watch whenever you want one. And completely guilty pleasure in the sense that it's not practical. I can still check the time on my phone just as well, but I like it. That's what a guilty pleasure is. I just like it. That's the point. But the real answer to your question is, of course, as many people know, is basketball. Like if you folks knew how many minutes of my average day was spent thinking about the Philadelphia 76ers, you'd be embarrassed for me. You would feel bad. You would think that I'm wasting my time. You know, I talk about lots of things on the internet and so forth. When I'm reading things on the internet, a lot of the time it's about trade scenarios for the Sixers, etc. And, you know, at the end of a long day, if there happens to be a Sixers game on, I'd be very happy to watch that, even though they're very far away. Technology lets me watch the games now. It's kind of awesome. Again, completely impractical, but pleasurable. And I think that's good. I don't think that you should feel guilty about it at all. So pleasures, let's just call them pleasures. And let's say that pleasures are good things. And with that, I cannot think of a better place to wind up this Ask Me Anything episode. As usual, thank you very much for supporting the Mindscape podcast. It's a great ride we're all on. And we have in this new year some pretty awesome new podcasts coming up. So stay tuned. Bye-bye.